mute for online.
Yes, sir. So, sir. So, shall we start? So now we are going to start the today's program. Today, as you know, we are going to organize an international conference on efficient engineering systems 2020. So, on the behalf of Jahan College of Engineering, I would like to thanks our management, Chairman Sir, Sri Tatya Sahab Gunjad, Director Madam, Professor Suvangi Gunjad Madam, our Chief Executive Officer Sri Galle Sir, and our college principal Dr. Garkal Sir. So we all welcomes to all the dignitaries who are joined along with us. Dr. Sarkar Sir, Dr. Munde Sir, Dr. Sunday Sir, Dr. Kotkunde Sir, we welcome all of you, sir. So, as you know, this will help to the participants a lot from this international conference organized by the Jain College of Engineering, Pune. So, without taking much time, I would like to invite for Saraswati Pujan with the hands of our principal, Dr. Garkal sir. Sir, over to you. Thank you, sir. Thank you for the start of the program with the Saraswati Pujan. Thank you, Principal sir. Thank you, Galle sir. Thank you, Mankar sir. So now I would like to invite our Principal sir, Dr. DJ Garkal sir. Please welcome our participants and please provide some guidance. Over to you, sir.
Distinguished keynote speakers, Dr. Sarkar, Dr. Yashwant Munde, Dr. Sunday, Dr. Nitin Kotkunde, Chairman of our Jain Educational Comprehensive Educational Institute, Sri Tatya Sahib Ji Gunjad, our Chief Executive Officer, Professor B.S. Galle, Director of our institute, Mrs. Shubhangi Gunjal Madam, Dr. Sandeep Kale, my colleagues and all delegates, ladies and gentlemen, a very good morning to everyone. On behalf of Jai Hind College of Engineering, Puran, Pune, I welcome you all at the International Conference on Efficient Engineering Systems 2020, organized by Jai Hind College of Engineering, Puran, Pune, in association with the Association of Engineering Researchers. We know today most worldwide research is focused towards the enhancing efficiency of the engineering systems. This international conference is a reliable platform for multidisciplinary engineering researchers to explore their research and reviews to the world by remote online presentation. The world is going through a rapid change, and across all disciplines, the research integrity has become increasingly important. Innovations and R&D, these are the key drivers of the economic growth of any country. This conference will provide opportunity for the global participants to share their ideas and experience, and will help the delegates to establish research or the business relations, as well as will find the international linkage for the future collaboration in their career path. In this international conference, there are 6 tracks or domains we have selected for the presentation. These tracks are electrical and electronics engineering, computer and information technology, mechanical and automotive engineering, civil engineering and architecture, agriculture, and a multidisciplinary domain. In this conference, we have received 81 research papers from 13 countries, and 191 authors have contributed for it. After single blind peer review process, we have selected 38 papers for the conference presentation. We are very satisfactory with the impressive work carried out by our scientific committee members, and keeping the acceptance rate of 46.91%. We hope that this conference on Efficient Engineering Systems 2020, The outcome of this conference will lead to significant contributions to the knowledge base in these up-to-date scientific fields. All research papers accepted for the presentation in this conference will be published in an open access proceedings with ISBN number. The conference proceedings will be submitted to all major indexing services. Some selected papers will be recommended for international journal and international book chapters based on the reviewer's recommendation. Some selected quality papers from this conference will be considered for publication in edited book to be published by the Central West Publishing, Australia. During this conference, all selected papers will be presented through the remote video presentation, and these presentations or these papers will be made available online on 10th October 2020 through the conference YouTube channel. I am happy to announce the following awards, which will be for the conference participants. These awards are: we will select 6 best papers, we will select 6 best presentations, and we will select 2 papers with quality research content. And these awards will be declared on 15th October 2020. Today, on the opening day, 4 keynote speeches on the personalities from the scientific field. These speakers are Dr. Achintya Sarkar, who is from NITTE Bangalore, Ashwant Munde from Cummins College, Pune, Sunday Oedipo from Prominent University, Nigeria, Dr. Nitin Kunde from BITS Pilani, Hyderabad campus. All these eminent speakers have significant contributions in research. On this occasion, I would like to take this opportunity to thank the organizing committee members and the Association of Engineering Researchers for their hard work and the efforts they have put in planning and coordinating this event. My special thanks to scientific committee, which is comprising of 76 members from India and abroad, and they are from reputed organizations and universities. Once again, I welcome you all for this international conference, and I wish everyone a successful and a fruitful conference. Thank you all.
Thank you, sir. Thank you, our principal, sir, Dr. Garkal, sir, to welcome all the participants, all the dignitaries. So thank you once again, sir. As you know, this program is broadcasting through the YouTube channel also. So uh, the live streaming is also being broadcasted at the our Jain College of Engineering YouTube channel, and we are this program we are conducting through the Microsoft team. So thank you, sir. Next, I would like to invite our academic dean and head of the department, electronics and telecommunication engineering department, Jain College of Engineering, Bhede madam, to give the introduction of uh, all the chief guests, all the resource persons today you are going to present. Madam, please over to you.
Thank you, Arya sir. Good morning, one and all present over here for today's conference on Efficient Engineering System 2020. I would like to introduce our today's keynote speaker, Dr. A.K. Sarkar. Dr. A.K. Sarkar has graduate and postgraduate education in IIT Kharagpur in Aeronautical Engineering 1975 to 80 and IIT Madras in Computer Science. During 1980 to 82, he worked in Hindustan Aeronautical Limited, Design Bureau, Bangalore. From 1984 to 2018, he worked as a scientist in Defense Research and Development Laboratory, DRDL, Hyderabad, and superannuated as a technology director, system director. Being in DRDL, he pursued doctoral study in engineering from IIC Bangalore. After superannuation in 2018, he worked as a visiting faculty in DIIT Pune for 1 semester. From August 2019, he has been working in Aeronautical Engineering Department of NITTE, Meenakshi Institute of Technology, Bangalore. His teaching and research interests are flight mechanics, simulation and modeling, control, guidance, estimation and optimization technique for aerospace application. Such an eminent personality is there with us. So I would like to request to Dr. Sarkar, please start the session.
Yeah,
His
madam,
title
thank
of
you.
speech is Okay, sir. Thank you. His title of speech is Evolution of Flight Vehicle Control and Guidance since Second World War of Second. Thank you, sir. Sir, I would like to request, please start the session.
Okay. I'm just starting.
Thank you, madam. Thank you, madam. Now I would like to Sarkar, sir. Please, sir.
Can you see?
Yes, yes, sir.
Can you see the screen?
Not yet, sir.
Okay. Screen share. Display window, desktop window. Acha. Share. Okay. Share. Can you see, right? Can you see?
Not, sir.
Can you see now?
No, sir. Yet not seen.
Okay. Stop sharing. What is that? Open share tray. Then desktop window. This one. Share. Does it make any sense? Is it okay now? Hello?
Sir,
can you see?
No, sir. No, sir.
What I'm doing, it is coming. I'm sharing now here. Open share tray. Okay, then what do you call desktop? Then I'm here. Your entire screen. Okay, share. Can you see, bhai? Hello? Hello?
No, sir.
Just a minute, sir. Just a minute.
I have done the way I did yesterday.
Yes, sir. Yes, sir.
देख सकते क्या अभी? Now you are seeing our
Your screen is visible.
screen is visible, na? Okay, thank you. So, I will start now.
Sir, please open your presentation.
No, that is from this is the thing from my side or your side. Hello.
Sir, here is not visible.
Then can you do one thing? Whatever I sent, can you just play that one so that I will talk from this side?
Okay, sir. 1 minute.
Because there is no point of wasting time.
Okay. Okay. क्या कर रहे हैं इनका प्रेजेंटेशन
Because I anticipated this, that it may not work. Just to show the screen, I will go one by one.
Okay, sir. Just a minute. I am sharing.
You see, there is some problem from my side. I don't know why.
Sir. Sir, now visible?
Yeah, now it is visible.
Okay,
Go to
sir.
the full screen and request you to go one by one. You just help me here. Sir, I didn't anticipate this problem will come, but anyway.
Yes, sir.
Yeah, you just make it a full screen. Okay,
Yes,
shall
sir,
I
yes.
start now? Acha, sir, very good morning to all the colleagues, dignitaries, and faculty members and students. And I have been delighted, and I thank the committee as well as Sandeep that this talk has been told me to give. At what I am going to do, I am not going to any mathematical equation, and this I felt that it will be generic in nature, just something like a history. I am everywhere. What you call? I'll start from the inception of the aerospace by Wright brothers and see up to today what are the what you call improvement, particularly in the control guidance point of view. It is there. Next. Yeah. So evolution of the flight vehicle I'm going to talk, that is aircraft missile. It is an interdisciplinary science. That's what I'm going to talk. And how over the years, the software and hardware blend of that has brought to the situation today. And we are going to talk about this latest technology, whatever. In a nutshell, of course, I'm going to talk. Particularly hardware, are basically inertial navigation system, accelerometer, gyro, global positioning system, radar, seeker, and guidance and control. And the control actually, this contains one element called actuator. This is basically a motor. Without these hardwares, software cannot be written, and hardware only always puts the limitation on the software evaluation or performance in the on flight. And then I'm going to conclude. Next. So I am going to talk about the evolution of the flight vehicle. All these things I have taken from different links on Wikipedia. And so just I am going to start from Wright brothers. Next. See, Wright brothers are basically the first people who invented the aircraft in 1901. And they are two brothers. And if you see the Wikipedia, what happens at the end, one of the brothers also died in aircraft sometime in 1961. Out of the two, but I think younger brother died. But they are the first who gave the breakthrough in a science, particularly in the aviation. Next. 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 Hello. Next. Hello. Next, yeah. So Wright brothers' technical contribution, basically they made the aircraft made out of the wood. This is the aircraft I'm talking about. It will be heavy. It was basically something like a glider. And thus, the first time when they made, no aircraft used to fall down after some time because of the lack of the stability and control. So first application came in the World War. Next. Next. Hello. Next. Hello. Next. Next. This is the World War I'm going to talk about. Hello. Next. Hello. I'm going to talk about the World War. So, hello. Hello. So fighter jets in 1970s, they came. Then they are the different F-16 and different type of aircraft, the fighter jets in between they came. And in between what happened in Second World War, it was invented and it was fabrication was made and they started using it. Particularly the Germans are very successful. And US people also made the fighter jets in 1970 with latest technology with control and guidance. The control guidance started that time. You know, that basically the controls are basically of the mechanical in nature, but they are not electrical in nature. Next. And see, commercial jet came in 1980s, but the first jet aircraft came in 1960s. That is the what you call Comet aircraft. You know that Comet aircraft had its own failures. In India also 1963 in Calcutta airport, one Comet aircraft crashed due to the fatigue problem. Then over the time, they have improved the structures and everything. And the Boeing 747 became one of the masterpieces, particularly for the aviation. And next, commercial jet. Next. Today, I'm showing you in the world, they are basically 380 and Boeing 747, they are having the capacity of 350 passengers. This is the best evolution has taken place in 2000s onward about the aircraft. And military aircraft also I'll show you. Next. This military aircraft, this is in the latest technology. What has happened? This is a stealth technology. That means from the radar, it has not been a question to see the aircraft at all. So now it starts with the basically dynamics in 1920s. And today, what has happened? Everything has been taken over to the software and electronics. Electronics means basically it will not been a question to see the aircraft at all. And from here, it is launching the Amran aircraft, Amran missile. So see, technology has come today up to this end. Next, you go. Next. Next, chalo yaar. So history of the missiles also I'm going to talk. India, the Chinese people, they started the missiles technology, and later in India, Hyder Ali and Tipu Sultan, they also used the same thing against the British people, and the British people really got impressed by using their rocket motor. So next. So this is the Tipu Sultan fought. He is the Sultan of Mysore. He fought basically against the British people, and he gave really resistance to them. So it had gone through so many years old, 17th century, particularly the rockets were made. Then subsequently, I'll tell you, in our country, VSSC, what you call bright future thing thought by our Vikram Sarabhai, and then after that, our Jawaharlal Nehru, what you call that gave instance. Next. So today, particularly this, it started sometime in 1960s and 1980s. The missile lab that Dr. APJ Abdul Kalam he came, and we have given up to, of course, Agni and Prithvi of a very high range and tactical vehicles of Akash, Nag and Astra. So in India also, space side as well as in the defense side, since last 40 years, over the years, we have improved. Okay, next. Next, you go. Next.
Yes, sir. Next. It's next.
Next, this is the missile. I have to finish up. Jaldi chalo yaar, because I think there is a. Now I want to say this missile aircraft What are they? Is it only one discipline? No, no way. Because see, I'll tell you, it will be missile will be having a propulsion, then guidance, control, navigation. These 3 units only I'm going to talk about. It will be having the warhead, structure, aerodynamics, configuration. So next slide, I'll show you who are the people who are involved in this missile or aircraft design. Next. Next. Next you go. Aircraft and missile, just previous slide here.
Yes, yes.
It is basically dynamics of flight mechanics, or this part is aerospace, fluid mechanics, mechanical aerospace, structural design, civil mechanical, navigation guidance. Those things basically, I'll tell you in my talk, it started basically in electronics department in during the Second World War. Today it had become it's an interdisciplinary subject. Sensor technology, it is a very important thing. Then packaging, this is also electronics people. Then came embedded system and detailed simulation, computer science and mathematics. Then, okay, so what I mean to say today, this subject is a completely interdisciplinary nature. Next, you go. Next. So, in what? Basic dynamics, that's what the did. And I'll tell you the name of some stalwarts whose thinking process became a breakthrough in the century. First came the mathematician, then came the physicist. One is Newtonian mechanics. Mechanics means F is equal to mx double dot Newtonian. Then after that came Lagrangian mechanics. Whatever the Newton did, Lagrangian did the same thing by using the energy principle. Ultimately, two roots, but they give the same solution, same equations it comes. So Lagrange and Newton, both of them were pioneered in this equation of motion. Anything, aircraft, satellite, car, anything. Newton's a Lagrangian method. Next. Next, you go. Next.
Yeah, sir, it's next.
Then I'll tell you, the mathematician invented those things and kept in the book. Physicists came and they tried to apply in our problem. So who is the next person? Laplace. He basically gave the Laplace transform, particularly for the solution of the differential equation in the algebraic form. Then Fourier transform. I'm just writing their names. Anybody interested, he can go to the net. He can get all the information today. Then came our John Frederick Gauss. He's basically the person, the probability theory. Any engineering subject, if you take, probability theory has to be there. That means it has to be worked. As an example, I'm giving a talk to you now. This person, what you call, my side failed, so I am taking your help. There has to be some backup, and with that, it has to work. Nothing will work ideal. So for that, probability theory was invented by Gauss, least square technique. Is there the fundamental of any science of a neural network, fuzzy network, everything you say. Then came computer. And computer, then von Neumann machine, von Neumann machine. Computer basically invented by Charles Babbage. Then von Neumann machine is the first concept of computer. Next. Next.
Yes, sir, it's next.
Next, here. See, this is the first computer. Sometime in 1946 it came, and you know that what I mean to say, that is in 1946, and today 2020. You see that during my days I used to work in calculator comes side rule in 1970s. Today we are having a laptop in the home and anybody can afford. How the technology has grown, it has grown exponentially. So that's why all the subjects also have changed. Next. I am going to talk about the impact of the software. Basically, I'm going to talk about the navigation first, then guidance, then control. I'm not going to talk about other discipline because this is the area where I have worked. And along with the software, there has to be a hardware, inertial navigation system, accelerometer, gyro, GPS, radar, seeker, all these things. I'll go. Okay, next, you go. Next.
Yes, sir, it's next.
Next, here. So navigation, guidance, and control means navigation means I am going from one place to other. Say from Bangalore to Pune, I want to go. So which way I'd go, that I have to think. Okay, then comes previous slide here. Previous slide, bhai. Then previous to this. No, एक minute. सामने वाला. Next one. No, next one. Next one. Okay, so now what I mean to say, it will be having the sensors. So sensors, okay, I am not talking about the slide, I'll talk on my own. So navigation means I am basically going from one place to other. And guidance means which way I'll be going. Like navigation means I have to go. So it will be having I go from one place to other. So kinematic information is there with me, position and velocity presently. Next means how to go. That is basically the guidance will decide. That means which route I'll be going. Okay, either I'll go via Bombay or by Pune. And then ultimately the innermost part is control. So what will happen, that control, what it will do in the flight vehicle, it will try to maneuver, or it will be having its own control. Basically for a missile, it is a fin, aircraft is a basically elevator, radar, and all these things. So with this, it will try to control. So it will go. But for that, what has to be there? One sensor has to be there. So today, see, sensor means I am telling you the accelerometer, gyro, all these things. But sensor will never work correctly. It will always giving some amount of noise. I'm telling you, one signal is there, y is equal to mx. The sensor, it will not get the exactly the same. It is not possible. And what will happen, there will be some amount of noise. In a voltmeter, if you see in the home, always 230 you will never get, 227, 232, like that. And from the position information, if it is so, you have to calculate velocity. See, if you calculate the velocity, what will happen? A lot of noise will come. So you have to do the differentiation. Once I get a position, one difference means velocity, other means acceleration. So you have to do the differentiation, and differentiation in presence of the noise is a chaos. That's what I'm showing you, the simple MATLAB plot. So people, how the people's invention came. Next slide you go. Next. See, initially Carl Friedrich Gauss, he what he called invented least square and recursive least square. And then after that, during the Second World War, Wiener, he was again a child prodigy. Both the people are basically child prodigy. He designed the Wiener filter in the frequency domain, and he removed the noise. Then after that, this great gentleman, Kalman, in 1930 to 2016, 58, he brought his first paper on how to do the thing in the time domain. The Kalman is basically the person whoever Wiener has invented the physics, and the same thing he has given a mathematical form. So he, by using this filter, you will be in a position to remove all the noise from the signal. Can you remove all? No. But whatever residue will be left with, we are trying to solve an engineering problem. With that, it will be in a position to do the job, and we are surviving on this. So Kalman is the person who designed a Kalman filter. Basically, for the navigation purpose, it was used to remove the noise. Once you remove the noise and get a signal, based on that only you can think about the control. So this is about Kalman. Next. Next. Hello. Next. Next.
Yes.
Yeah, chalo yaar. So application of the estimation theory, I am just, because of the lack of time, I am not talking. It starts sometime in 1802, but particularly to see the astrodynamics for see the satellites. One satellite, Piaggi from Italy, he happened to see. But later, all these information, the Kalman's least square, then Fisher invented maximum likelihood, Wiener filter. With all these things, Apollo space mission took place in 1966 to 71. Then Kalman's theory became a breakthrough. Before that, his paper was in the dustbin, was lying as a paper. So after all the Apollo space mission, when they did with the sensor, they removed the noise. Those days sensors were not like this. They were basically something like analog sensors and all. So I'm into the 1960s. So application of this filter came in different aerospace problem, and it became an interdisciplinary topic. Today, in aerospace department, chemical engineering, mechanical engineering, everywhere they take a course, whoever interested in this side, and he'll be taught. Next. Next. Hello.
Yeah.
So along with this, what happened that there is an invention in computers also. 1906, 100th century. This is basically equation of motion of Kepler. Then came Newton. Newton gave it differentiation, integration, and calculus. Then came 1806. It came the Gauss. Then came Fisher. Von Neumann machine in 1940. It was invented. Then after that onward, the breakthrough of the science. And today, any control, guidance, aerodynamic structures, everything depends on the computer. So with the computer evolution, this subject become popular in the all discipline. Today it is not a technical department. It is in any discipline. It basically comes from basically applied mathematics, and everywhere people are using this now with the advent of the computers. Next. Next, chalo yaar. And yeah, application of this Kalman filtering basically in the guidance and navigation. Actually, what happens that the system will be having some noise and bias, and bias has to be removed. I'll give an example and show you. So Kalman filter was used to remove the noise and bias and to calculate the derivative from the position to calculate the velocity and acceleration. And you can ask me the question, can you get exact? No, but you are an engineer. You are not trying to get a mathematical solution. Whatever amount of accuracy it does, it will do the job. Like using the Kalman filter, when the target goes to the missile comes to the target, say around some 10 meters, it will be coming. It cannot go and hit, impossible. It is a physics. So it will be having its warhead. Warhead will be very high warhead, and with that it will blast. So when your job is to come somewhere close to the target, maybe around some 10 meters, then warhead will blast. If it goes to 20 meters, then what will happen? Warhead of better quality has to be used. And generally, ICBMs and all those things, warhead is not a problem because they use the nuclear warhead. And basically, if it happens, so for that, what you call this error of 100 meters is not a criteria. So that's what I mean to say. So with this, we're in a position to get a solution in the real life problem. So navigation is basically important. Is very the Kalman filter has gone INS and GPS together. How to integrate and reduce the errors in the INS. Those things only I'll talk. Next. The brief theory about the navigation. In our Sanskrit, navi means boat and gati means motion. And this from what you call this basically came from the Roman or Italian words. Our and main sensors for the navigation is basically inertial navigation system, and today is the GPS. So today, what the people do, you take INS and GPS together. GPS is a very cheap device. So it has come to the common level today in our phone also. So from the GPS, technology has gone to that level. So GPS and INS they took and they use to do the navigation. Next. This is what I am telling you. One INS unit, it will be having the accelerometer and gyro. This is the dabba. And come inside. Go to the next slide. Go to the next slide. So it will be having the accelerometer, and this is the gyro. The whole thing in a missile, it will be something like a small dabba with around 12 centimeter by 6 centimeter by 5 centimeter. So it has come to such a miniature level. This has happened because of the evolution in the hardware. So hardware and today the MEMS technology has come, and MEMS technology really making the wonders. They're making the small things with a very powerful stuff inside. Okay, some errors should be there. Inherent errors should be there. That is removed by the software. So it is a basically combination of hardware and software both. What is doing the wonders today? Hardware price is coming down slowly, and software complexity people are in a position to handle in a better way because of the implementation of in the real time in the computer. Next. So simplified block diagram of inertial navigation system, I'm telling you, it will be sensing the acceleration. Integrate once more, you get a velocity. Integrate one more, you get the position. That's all the accelerometer works. Next, INS works. Next. So these are the navigation routes I'm showing you during olden days, BC. But later, how it involved, I'll finish up in 1 or 2 slides. Next. Hello. Next.
Yes.
So different navigation methods. The pilotage. This is use a fixed value of reference. Those days in the BC and the ancient what you call center of this is AD. The Christ era means T, and BC means before Christ. Then came dead reckoning. That means at any particular time you know the position, you have to you have to calculate and predict the velocity. And today what has happened? This radar navigation, inertial navigation, radio navigation in between, it used to be 1950s. And then came radar navigation, means you will send the signal from radar, it will go and hit the target and come back. So you find out the time, and accordingly you see how far it is. Then came inertial navigation, and in 1960s. Then today it is basically satellite-based navigation. Use artificial satellite in the determine the position. And today the combination of inertial navigation and satellite navigation, it gives the best possible accuracy. Next. Hello. Then modern period 1950 to 60, that Sputnik, actually Russians are the first people to send a vehicle in the space 1960. Then after that the Americans started, and Russians, they're the first people, Sputnik by them, 1960 to 70, concept and development of satellite navigation. Then in between, after the Apollo space mission, Americans became very enthusiastic and they started diverting their fund in the satellite. And in between, this gyro became much better. Hardware-wise, ring laser gyro. then fiber optic gyro. These gyros became very popular and with a very good precision and than olden days. And so that's how the navigation hardware items people are improving. Particularly here, the Germans contributed a lot. Next. And during 80s onward, this GPS or Napster, Global Positioning System, this concept is basically by Americans. And now, 1990 to 2000, they are using the MEMS technology. MEMS technology means size has been minimized. And 2000 to 2010, what has happened? Global GNSS, basically they are by the European people. GPS as well as this is basically by Americans. And India is making now Gagan, that India is making. So with this satellite navigation, today all the errors have come to minimum. And so this is a what? Culmination of the hardware and software both. So next you go, satellite navigation. I'll give some example. Hello.
Yes.
So 24 satellites are there at any particular time, 4 if it is there, so then it will be in position to calculate the position. Latitude, longitude, they are convert to X, Y, Z. So it is done by the hybrid navigation. That means INS and GPS both by using the so-called Kalman filtering. Next. Next. See, I am just giving an example for a missile. I did the work and INS and GPS. Suppose INS is there alone. I'll tell you, INS will be having a bias of around some accelerometer bias of 1000 micro G. 1 G means 10 meter per second. 1000 micro means into 10 to the power minus 3. So very low value, but surprising, that you take it. Position what? Half into 80 square. You go for 300 seconds. Any missile goes for around some 2 minutes, 3 minutes ICBMs. So then what happens if you multiply, half into 80 square, if you calculate bias from their position, it will come to around some 1.5 or 2 kilometers. In the, for a Prithvi class of missile for 400 seconds I have taken. So if you don't, if you don't use the GPS, this error will grow. Now use this as a GPS as a measurement, and from there you correct the bias. You see that bias comes to around 50 meters. So 1500 meters to 50 meters because of this Kalman filtering, which is basically software, and the software is sitting on the hardware OBC onboard computer, and it is correcting it. It cannot come to zero. But as an engineer, you're not bothered about the zero because everywhere in the real life there is some amount of approximation has to be there. You cannot make it zero. Okay, it is just not possible. So this is the great contribution of the people, what has made the people today to use this INS and GPS integration. So today you see the UAV, it will be having INS and GPS both. INS is basically MEMS INS. So you know that the whole cost is around some not more than 40,000 rupees. And the same INS, if you want to put in the aircraft, that comes to around some 2 crores minimum. Any missile INS is around some 2 crores. So the price varies between because of the MEMS technology from 40,000 rupees to 2 crores. Now it's up to the software to see handle it properly. So software, what will happen that good quality INS, if it gives you with the GPS, gives you around some 5 meters. Bad INS with the GPS will give you maximum 50 meters. And UAV and all 50 meters of error is okay. People accept it. So that's how over the time in today what has happened, that the price of the hardware has fallen down. Then software also, people have in complexity. They're in a position to tackle the more challenging problems because of the computer today. And the combination of the both is giving the optimum result. That's how. Next. Radar-based guidance also. This is a say Akash missile and this is the target. So ground radar is there. So radar data will be there. They will filter and send it aircraft position. You will send it to the missile. Filter data based on that guidance will be there. Control will be there, and it will be hitting the aircraft. So here also. Next. I am just showing you how the radar works. This missile from the aircraft it will go and it will hit the target using radar-based guidance. Next. So okay, next, chalo yaar. Next. Now radar means from the ground you have to see the target. But if it is for the seeker is basically a radar inside the missile. So seeker means once they launch the missile, it will be autonomous. I'll give an example after some time. So once it's autonomous, it will do a latch into the target and it just go and it will hit. It will be completely in the autonomous mode. So radar-based seeker, active radar seeker, and imaging infrared seeker. Here means noise is less, but here the noise is more. So people are using both, particularly infrared seeker is basically for using the small range missile, and radar seeker is basically for the larger missile. Okay, big range, by some 200 kilometers or something, then only those active radar seeker is used. Next. So, that from the missile, the signal it will go, it will hit the target and come back. It is basically radar principle only. Next. 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 What I want to show you. Next. Hello. You see, I am giving a real life example. We had a seeker flight of a missile called Astra. So the information, this is LOS rate, it is so much noisy. You just see red color. Then after, after you filter the data, it becomes so smooth. That this is what is doing. Only the software can do this job. So if it is a very good hardware, I don't need a very good hardware. Very good hardware means more costly. You take a moderately good hardware and you improve your software so that the blend of the two will give you the most optimum result. That's what. So this is the type of data is there, and this is the blue line, and the green line is basically the filtered data, and this was used for the missile. So that is the job of this navigation. Is this next? Missile components and all. Okay, I will skip this. Okay, so and next you go. Next. And now this comes in the outermost loop, guidance, and then now it will come the innermost loop, the guidance and control. See, I am giving an example of a air-to-air missile. So this is what do you call this aircraft is launched from the missile is launched from the LCSA. It will be having a range of around some 100 kilometers. So initially it will be going by using the mid-course guidance by radar. So that will go up to 80 kilometers. And then after that, when it will go range to go goes to around 20 kilometers, then seeker will lock on. So while in the initial phase, the pilot would be eliminating the target. So you need some secondary help. But once the seeker locks on, seeker it is used in the terminal phase so that it will be autonomous mode. In the meantime, pilot will fly away and it will go and hit the target. So this is the combination of both. So mid-course and terminal. And this guidance started during also in the World War II. Actually, Germans are basically the people who invented this guidance, but somehow they didn't document. So what important is the documentation. Later in 1950s, Americans developed it, and today everybody knows the Americans have developed this guidance, PN guidance, proportional navigation guidance. It is basically something like a PID controller. But the German, because they did not document, their name is not anywhere. But they are the people who did this. They used it in the World War II. Next. Hello. Next. Next. So, yeah, control theory, I want to say, again, necessity is the mother of invention. What I mean to say today, this pandemic has come. Could you think that we'll be in a position to talk online? Initially, some hiccups are there, but I'm very sure it will get streamlined. So similarly, aircraft, when the, what do you call this, German people, they developed the aircraft and missiles in World War I. But in the meantime, these American people, what happened? No, they started working on this, and the people basically guidance and control. I'm not talking about the other discipline. Other discipline also same evolution took place. So first, people dawn of control theory started in 1930, and you won't believe that it started with aerospace. Other discipline people are using today in automobile or anywhere, like say washing machine, everything, but it started in aerospace. But particularly 2% called Harry Nyquist. He was born Sweden time. He's basically Swedish American scientist. He developed the stability of the feedback system, and along with him there is a person called Henry Bode. He also, I given him the time of death. What do you call? These are all even in the Wikipedia. They are the basically father of the control. Those days there was no computer, and I'll just tell you how they did. You think so? What happened that those days only slide rule. But log table was there, log table and slide rule. Using the log table and slide rule, they use the mathematics that solving the ordinary differential equation, but they want to use Laplace transform. So using the Laplace transform, you can come to the frequency domain, and then calculation becomes very easy. You don't have to solve any differential equation. Then what happened? They use the Fourier series. Fourier series also was developed by Fourier. That means any time domain, you take it as a summation of the frequency components, sine and cos. And one sine and cos signal you take, you will be in a position to handle. And as you know, any signal in the time domain, basically, it will consist up to 4 hertz or 3 hertz. Okay. So if you can handle all the input-output relationship, 3 hertz, 4 hertz, what you call any signal, exactly, you'll be in a position to track. Contribution of these 2% is phenomenal in the control theory. That happened in 1930, and you'll be surprised to know even today also, after this Nyquist plot and Bode plot, Bode's work, everybody goes before the flight clearance, how much is the gain margin, phase margin, invented by Boeing. The people work in the Bell Lab. And then ultimately, aircraft industry they used. Then modern control came in 1950. Kalman's contribution, I told you. One more gentleman, he from Russia, Lyapunov, Russian mathematician, theory, all this gave rise to modern control in 1950. After the Apollo space mission became, started having lot of input, putting lot of fund on the modern control. This modern control also works in a limited sense. You'll be surprised to know across the globe, they do the basically classical design by using the modern approach. But the nonlinear control, all these things have come, but they are on paper. Nobody tries to take a risk because of only one reason. The person who and Nyquist, these two people gave a concept of stability. How much stable you are, what you call before the flight, that comes from something called Bode plot. And that thing, nobody can replace even today. And nothing equivalent to that has come. So you do the any analysis you do or design you do, maybe non-linear, but ultimately come back to equivalent linear theory and try to calculate the Bode plot. So then once you're having 30 dB gain margin of 6 dB, and 30-degree phase margin, your missile or any aircraft will be clear for the flight. So this, particularly these two persons, their contribution is phenomenal. And I am very sure, even after we die, after 20 years, 200 years also, unless now new theory comes, they are that you design a control. Know how much amount of robustness you have. That robustness feature you just gain margin, phase margin. So though it has come, but their concept has not been thrown out. Everybody using theirs. Next. So missiles I'm talking, but anyway, I'll go slowly, one by one. Skip guidance. I'm not going to talk. So another. So this is the guidance I told you. This is the boost phase, mid course, and terminal phase. Next. Then okay, this is the terminal phase guidance, PN guidance. Next. So here I want to tell you that it's a basically feedback system. This is the only one place I have used the equation, but this is a fundamental equation in a control system. Output by input is basically this by 1 plus GS into HS. Here you see there is a hardware, and here also hardware. So control system, anything on my own, that will be dictated by actuator, the hardware. Sensor will sense the output, and actuator is given the command to this. It will drive the servo, be giving the deflection in the fin. So the this mode is that become unstable. This becomes negative, 0. So once this becomes 0, so that means magnitude becomes 1 and phase become 180 degree. So from here only, magnitude means gain and phase means phase. Gain or phase margin, gain margin, phase margin has come. And if you want to give in such a way, you should have to be phasing a gain margin, and this concept replace. Okay, next. Hello. Next. Yeah. So actually, application of the control theory basically in the tracking problem means lateral autopilot, engine control, fighter aircraft maneuver, satellite orbital transfer. All these are basically application of control in the aerospace problem. That is then cruise control when you are going. Suppose from Bangalore to Pune, I am going. So what will happen after going to 5,000 meters or 5 kilometers? Pilot will put it in the auto mode, and he will see that your height control means you should be always height to be 5 kilometers. So this is called cruise control. Attitude control means when you climb, attitude should be 15 degree. So this is called attitude control. So everywhere the implication of there. But what is the constraint is basically my hardware, actuator as well as my sensor. So these are the different vertical stabilizer, then fins and aileron. These are all used basically for the control. These are the hardware. You have to design the control in such a way you should be tailor-made for your available hardware. Otherwise, what will happen? You have to buy very costly hardware, and ultimately cost will become very high. And everywhere, if you see at the end of the design should be less costly. It should be cost effective. So hardware and software means it is a human one person's job, but hardware means it's a many people's job. So developing a hardware is much more demanding and more difficult than a software. Next.
Yes, sir. Yes, sir.
Yeah, chalo yaar. So some magical features of control theory, what I told you, that basically it was invented during the log table slide rule days, and even today also, because of that concept, and it is so simple to understand, visualize 6 dB gain margin and 30 dB phase margin. Only if you have, then they will give the clearance. So after modern control has come, nobody can replace the classical control. What I mean to say, science is like this. They have understood through the physics, not through the mathematics. Next. Next.
Yes, sir. Control system.
So different control systems in a aircraft or missile, aerodynamic control, thrust vector control, all these things are there, and reaction control, these things are there. Next. Chalo here. Hello. These are the things. I'll skip and I'll come to the actuator. Next. So these are all different controls they use, and so they are basically the hardware. Your control law has to see and obey the hardware. That's all. Next. Next. Then actuator. Actuator is basically you give a control demand of the delta of fin of around some 10 degree. How fast it can get that 10 degree, that is done by the actuator. The actuators are hydraulic, electromechanical, pneumatic, and MEMS. MEMS actuator has become very popular, but definitely they are less cheap, but they are not that accurate. So only for the UV type of application only they use the MEMS. And aircraft and all, they use only the hydraulic actuator. And missiles, they use electromechanical. Actuators are basically it is a what do you call, it is a basically servo mechanism. What puts the control law means digital data to a realistic hardware deflection. This is the actuator. It is a very important part in a missile control system. Next. So I have just given the block diagram. Here also, it will be having this PID controller, D2A converter. So here also, basically from the electronic circuit, it is going to the mechanical. So D2, digital to another converter, and A2D converter will be there. So here also, electronics as well as mechanical will be playing the role. So actuator is a basically motor and source of energy, electrical current, hydraulic fluid pressure, pneumatic pressure, converts the energy into the motion by D2A converter and A2D converter. Next. I just show you the figure of one actuator here. Actually, I have taken from Wikipedia in different places. Somebody who is reading, you can just take it and go to the Wikipedia. You will get a lot of information. Next. 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 Another 2-3 slides more here. Next.
Missile target.
So the samne chalo next slide, another 2-3 slides more, because I have to finish another 11-8. So at the end, I'm telling you what has happened, that evolution of the flight vehicle. I started with aircraft and aviation. Okay, then I am telling you it has become an interdisciplinary subject. In 1980s onward, it has become interdisciplinary. Then what I mean to say, after the software developed, wonders are being done by using only the software and hardware. So hardwares are these. All the softwares have to be tailor-made according to the hardware. They are only the they are only the engineers. Ingenuity comes in picture. Mathematicians have developed all the equations many years back. As an engineer, what is your job? Your job is to see that write the software in such a way so that it will be compatible to the hardware. And hardware means inertial navigation system, accelerometer, gyro, radar, seeker, and then ultimately today is basically the MEMS. That's why UAVs have become so smart UAVs now, because of the chip. And similarly, actuator also. At the same time, I'll tell you one thing. This is the thing. Necessity is the mother of invention. It is true here also, because had the sensor been ideal, control engineering would not have developed at all. And had the sensor been without noise, that means it is without noise at all, then this subject would not have been there. In the 1800th century itself, means it would have been, that field proven, and it would have been very good. So in a reality, in the physics, and similarly for control also, control would have been ideal. But because the hardware coming in picture and the engineering coming in picture, so that's why only it took so many years to develop. So at the end, I'll tell you one thing. It is not the hardware alone. It is not the mathematics alone. It is the combination of hardware and software. And ultimately, who is the person who is dictating the terms of the physics? Mathematician is giving all the solutions, and your job is to see, understand, and you have to use it. So today, both the fields have improved, but still software improvement is much more. So today, people rely more on the software. Next. So if I have finished that, then go to the next slide, that I have to give acknowledgement to the people. So core committee, I want to acknowledge and thank that they gave me the opportunity. I never knew that I just, for the heck of it, I just sent the paper the office told, our college told. So now I see that they gave me a chance to give a talk. So I have to really thankful to them, so that you had a patience hearing to whatever I told. Okay. So this is one thing. And next slide I'm going. That next, I thank you all. And this, whatever I told you, I have learned in over 40 years. So there are so many people who have contributed to my understanding. So these are my, he's my guide, Professor Ananta Sainam. So under whom I did my PhD, and Dr. Vatsal is two people whom I learned. And subject, basically, I had to switch over to this area because of the organization requirement. So then other people also, my colleagues also, they help. And motivators behind my research, who are the people, I mean, some of them have expired. And this Manglurkar, I'm in touch with still. And he's a person, means he really helped me to understand the fundamentals. So wherever I go, I don't forget to put their names. So I thank you very much for listening to me. But anyway, with the given available condition, means I had to finish up. I could not show my slide. I don't know why. So I had to depend on you guys. So excuse me for that. And I really thank you very, very much for giving a chance to talk, and to management and all, and particularly for Sandeep. Whenever I was in trouble, I used to be in touch with him. Okay, so I hope that later this thing will improve. So had not been coronavirus, not been there, this job would not, this technology I would not have got. So I thank you very much. I thank you very much.
Thank you, sir. Thank you very much, sir, for giving the very important information. So, sir, before leaving, I would like to our principal, sir. Sir, please give the appreciation note.
No problem. You have given me the chance to talk, that itself. Thank you, sir. Thank you. Thank you.
Sir, Garkal, sir. Okay, sir. Okay, sir. Thank you. Thank you very much.
Thank you very much. Thank you very much. Thank you very much. Bye.
Thanks.
Good day. Good day. Good day. Good day. Good day. Bye.
So thank you very much, sir, Dr. Sarkar, sir.
Thank you. Thank you.
So, shall we proceed, sir, next?
Dr. Sarkar, sir, I'm really appreciate from Jai Hind College of Engineering, Kuran, that you have given such your valuable time for us. Thank you, sir.
Thank you, ma'am. Thank you. Thank you, ma'am. May God bless you.
Thank you, sir.
Bye. Bye. Bye.
So, according to the sequence, I would like to, Bhede madam, please give the introductory part of our keynote speaker second.
Thank you, Arya, sir. Now I would like to introduce our today's keynote speaker, Dr. Yashwant Munde. Dr. Yashwant Munde has completed BE Mechanical in 2006 from Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, MS and MTech from Veer Mata Jizabai Technology Institute, Mumbai in 2009. He has completed PhD in the area of natural fiber reinforcement composites at the University of Pune. Currently, he is working as the assistant professor in Department of Mechanical Engineering at Cummins College of Engineering for Women, Pune, Maharashtra, India. He is having 12 plus years of teaching experience, including 1 year research assistant at Feast Software Private Limited, incubated company with IIT Bombay, Mumbai. He has completed one research project of grant rupees 3 lakh, and has going research grant of rupees 13.24 lakh from AICT Government of India for developing a composite material laboratory. He has 20 plus publications, includes the journal articles in peer-reviewed journal like Polymer Testing, Journal of Reinforced Plastic and Composites, Material Research Express, Advances in Material and Processing Technology, a book chapter and conferences too. He has worked as a reviewer for international journal as Polymer Composite, Willy, Materials Research Express, and Iranian Polymer Journal. Also work as a national scientific committee member for International Conference on Advances in Material Sciences. Such an eminent personality is with us today. He will provide the keynotes on micro and macro mechanical modeling of composites. So I would like to request Honorable Y.S. Munde, please start the session. Sir, please.
Yes, sir.
Okay.
Very good morning,
Yeah,
sir.
am I audible, sir?
Yes, sir. Over to you.
Yeah, very good morning. Okay, thank you. I'm sharing my presentation. Just give me a second.
Yes, sir.
Is my screen visible? Slides are visible?
Not, sir.
Okay. Now?
No, sir.
Okay.
Yes, sir. Now visible.
Now
Yeah,
it's visible?
Yes, sir. Yes, sir.
Okay. Is the slide mode is visible to all of you? Yes, sir?
Yes, sir. Yes, sir.
Okay. So very good morning to one and all. I am Dr. Yashwant Munde, likely to discuss some of the experience to the participants of International Conference on Efficient Engineering Systems, ICES 2020. So my discussions will be on the topic of micromechanical modeling of composites, and this micromechanical modeling of composites through a method called RVE, that is representative volume element method. So the outline for my session discussions is overall what is mean by composites, what is the way we have a material modeling to be carried out for these materials, then what is the context of micromechanical modeling of unidirectional laminated composites. And then I will discuss about a methodology that we use for a modeling, micromechanical modeling of composites, that is a RV method. So in this method, I will explain you about how we can prepare the RV, how we can apply the boundary conditions, what are the constituent equation we may use it, and a sample ANSYS APDL part program for getting a solution of this problem. And then few of the case studies I will explain you, and what are the other micromechanical models are there for other than unidirectional laminates that I will discuss. So basically, composites is nothing but a combination of two or more materials together for a third useful material. So if you add two materials together at a macro level, and if you are using a third useful material which has a better properties than the constituent, then we call it as a composites. So we have a reinforcement, which is the one of the constituent, and the matrix, which is I will focus the restriction of discussions only a polymer matrix. So there are a type of matrices can be used in a composite as polymer matrix, ceramic matrix, or metal matrix. So if you are using a polymer matrix and you are using a reinforcement and you are forming a form of material that we call as a composites. So what are the different type of polymers can have it? So polymers can be of thermoset base or thermoplastics. Thermoset, those are cured at a room temperature, and thermoplastic, which is to be cured at an elevated temperature. And what are the type of reinforcement? So reinforcement can be of fibers or fillers. So fibers can be an example where the L by D is very high, and the fillers where L by D is very small. So it's all about the aspect ratio. If you're having a high aspect ratio in thousands and hundreds, then we call that as the fibers. And if you're using an aspect ratio of a reinforcement material which is less than 10 or in very small amount, then it is called as a fillers. So these are the few of the examples I have enlisted for the thermoplastics like polypropylene, polystyrene, polyurethane. Thermosets type of polymers can be a epoxy polymer, polyester, vinyl ester. Type of fibers we can use as a reinforcement can be a glass fiber, Kevlar fiber, carbon fiber, and natural fiber also. And if you want to make use of fillers, can be a carbon nanotube, graphite, nanoclay, and so on. So these are the few examples of the type of polymers we can have and a type of reinforcement we can have. Now, if you see the class of composites, if you see the total division of composites can be in a three different class. One is a particulated or particle reinforced composites. Second one is a fiber reinforced composites, and third one is sheet molded composites. Now we are going to have a focus on this fiber reinforced composites. Now, what is mean by fiber reinforced composites? Where we use a long fiber or a short fiber. Those are having a certain length and a diameter. So there is a certain greater aspect ratio or having it with the reinforcement. So we call it as a fiber. Now, fiber reinforced composites can be of two types. One, a continuous fiber reinforced composites and discontinuous fiber reinforced composites. Now, what is mean by continuous? Continuous, they are very long. So length is very long enough in meters, and you can able to make to be put on the mold. So they call it as a continuous long fiber. Discontinuous, where they are a fiber but length is very short. So for example, in 10 to 20 millimeter or less than 100 millimeter is the length. So we cannot place them in a mold as a long portion. So they are going to be called as a discontinuous type one. Now, continuous can be of a based on the way we are making to be attained, they add them to with a matrix, they can be called as a unidirectional. Now, what is mean by unidirectional? If you are using a fiber in a one direction only. So if you see, this is my one fiber, the second one, third one. So all they are in a one direction. That is called as the unidirectional. Bidirectional, we have a first layer which is of direction 1, that is we call as the 0 direction, and second direction we call as a 90. So perpendicular to the first. Or you can have a multi-directional too. Not necessarily only along a 0 and 90 degree angle you have it. You may can add a inclined orientation plus 45 degree, minus 45 degree, or whatever the angle you want. So this is what we call as a continuous long fiber. What is discontinuous fiber? They are can be of aligned or randomly oriented. Aligned means what? In a phase of a matrix, they are perfectly aligned. They are short, but they have a perfect alignment. So that is what we call as aligned short fiber reinforced composites. Okay. And the second type, which is a randomly oriented, what we have, again, it's in a phase of a matrix, but the condition, they are short, but they can be of any orientation as per the, there is no specific orientation to be specified. So they are randomly oriented. That is what we call as a short fiber, randomly oriented short fiber reinforced composites. So this is what is mean by a class of composites. Now today's discussions, we are going to limit it only about a unidirectional fiber reinforced composites. How we can make the models. Okay. Now, if you want to analyze the material, the type of analysis you want to carry out, if you are going to analyze a composite material, so the material should be followed a generalized Hooke's law, which is for 3D constituent equation. So we have a tensor or a vector which is about a stress. So these are the sigma 1, sigma 2, sigma 3 are the normal stresses, and these are the shear stresses, is equal to, we have a matrix which is correlating to your stress vector to a strain vector. These are the normal strain, and these are what we have a shear strain. So relating a normal stress and shear stress to a normal strain and shear strain, the matrix which is relating it, that we call as a stiffness matrix or stiffness tensor. This matrix also called as a CIJ matrix. Okay. So this is a generalized Hooke's law which is used for 3D constituent equation. Now, the type of composites can be of, these are type of materials. So composites can come under a category of a first 4 type of composites. One, anisotropic composites, monoclinic composites, orthotropic composites, or a transversely isotropic composites. And very well known material, these are the metals which will come under the category of analysis of materials as an isotropic material. Now, how they classify? So it's all this classification of materials or material type is based on how your stiffness matrix is there. Okay, so if you take isotropic material, we have only a 2 independent elastic constants. That is, one we call as a E, that is Young's modulus. Second one we call as a Poisson's ratio. These are the two only independent elastic constants you required to know. And the third one, that is the shear modulus, that you can calculate by using the first two independent constants. But as you go on increasing the complexity of your problem of a composites to be analyzed, there is a change in the number of constants required. So if you take a transversely isotropic where we require 5 independent elastic constants. If you go for orthotropic material where I have a two plane of symmetry, we require to know the 9 elastic constants of the material. Now how this 9 came? So we know that for isotropic we have a E, mu and G. So for this is same in all the direction. Isotropic properties are same in all the direction. So we have only 3 constants. But when you go for orthotropic, the property along the direction 1, property along the direction 2, and the property out of the plane is different. So properties are different in 3 mutually perpendicular directions. Because of that, we get to know how many constants, 9 constants to be known. That is E1, E2, E3, mu12, 23, mu13, and G12, G13, G23. So each property along each direction, that's why they are came to a 9. When you go for a monoclinic type of material, instead of two plane symmetry, we have only one plane symmetry. So there you require a 13 number of elastic constants to be known. And if you go with anisotropic, which is the most complex type of material, we should know 21 elastic constants of the material. And all these constants are a part of this your stiffness matrix, or also called as the CIJ matrix. Now, this is all what about the composites and what are the level of analysis of these composites. Now, if you want to model these materials, now the classification of these material models is into 3 different categories. One, a nanomechanics problem. Second, a micromechanics, or third, macro and structural mechanics problem. Now, how this class is developed based on the length of scale of your problem or length scale of your. Yeah, am I audible, sir? I just want to get back.
Yes, sir, audible.
Yeah. Okay, thank you. Yeah. So the type of material modeling is classified into a problem of nanomechanics, micromechanics, and macro and structural mechanics is based on the length scale. So if you're having a length scale, it's 10 raised to minus 8 meter. 10 raised to minus 8 meter, type of problem is going to become under the nanomechanics problem. If you have a 10 raised to minus 6 meter as the length of your structure, that will come under the problem of micromechanics. And if you have a 10 and above meter, the problem will come to a macro and structural mechanics. Now, there are sub methods which we can use for solving of this category of problem. Now, today's discussion is on micromechanics, okay? And the micromechanics problem can be solved by using an analytical approach or a computational approach. In analytical approaches, there are certain equations available in the literature. Those you can use it. For example, a rule of mixture, that is one of the theory, inverse rule of mixture, Halpin-Thesis, and so on. There are numerous equations available, but you require to know more number of parameters for using those equations to analyze the material. Whereas the other method, which is a computational based, and which is we are knowing that nowadays there are very proficient computational techniques or tools are available, so we can make use of it. One of them is called the finite element method, in which we are going to see the RV method, that is representative volume element method. So we are going to understand how we can make use of this method for solving a micromechanics problem of composites. Okay, now why you require this material modeling for the composites? If you have seen before, that the composites where you have a requirement of large number of material properties. So if you take orthotropic, we require at least 9 elastic constants to be known. So the requirement of material properties is very large. So there is an alternate tool you should have, which will help you to get analysis of the material. Secondly, if you want to have all the materials that you develop, if you want to make use of experimental techniques to be used, that will become a tedious and expensive process, because for each of the type of material that you wish to develop, you have to fabricate and test it. So it will cost you more if you go with the experimentation. So, and along with that, if you see, there are n number of parameters which are altering or which are affecting the properties of your material. So if you have a volume fraction of reinforcement, one material, composite material, in which we have a 10% of reinforcement, another material we may have increased the 20%, 30%. So there are n number of combinations possible when you are going to combine the constituents. And even not the combination, but you take the constituent properties also. One of the composite, you have a glass epoxy. Instead of glass, if I wish to make use of a carbon, so at the same time you again go back to the fabrication of those new form of material, do the experiment and see the what is the effect of that. So it is a tedious and expensive process. So there is a complementary process that is to be there to the experimentation. It cannot be a complete alternative. Please note, it cannot be a complete alternative. It is an complement to your some of the experiments, and that what we call a micromechanical modeling technique. And this micromechanical modeling technique will give a approximate values of composite properties. So if you are knowing some of the material tested, and if you want to find in between compositions of the material, what will be the property, we may use a micromechanical modeling technique, which is also called as a homogenization technique, for getting a values of or properties of those composite materials. So that's why we may use it. Now if you see the complete any type of composite, so this is I just want to show you the picture. That's the way we have it. So this is a simple coupon specimen. This is a rectangular coupon which is made up of composite. Now in this composite, which has a length, width and a certain thickness. So if I take extracted view of the thickness, so you can see that there is a multiple layers in between of this. So what is this? So this is the n number of layers. So this is a layer number 1 of a reinforcement, and this is a layer number n. So you can have n number of layers from 1 to n to form a certain composite that you are going to fabricate. And if you analyze this material at a laminate level, this is what we call as a laminate, which is formed by using a layer by layer stack. So there are n number of layers stack which are combined together, and we are going to analyze this problem that we call a macro scale analysis of composite material. Is there any problem, sir? Okay. So what is a micro scale analysis? Now, if you are having one layer of composite, that is a lamina of composite, and this layer have a certain reinforcement material and which has a matrix material, and that we want to see how its property is going to be. And that type of material analysis we call a micro scale analysis. So if I take a small portion of this lamina, this is going to be a view that we have it, in which this green portion that you see it, it's a matrix portion, whereas this white portion are the fiber portion. And when they combine together, fiber and matrix combine together, they are going to form a one lamina of your material. And how the properties of lamina, if I know the property of fiber and if I know the property of matrix, what will be the property of single layer material? If you want to know the single layer material property, this is the way we call it as a micro scale analysis of the problem, or micro scale modeling of a composite. Now, then micromechanical modeling of this unilaminates or unidirectional laminated composite, how it is to be carried out. So if you take a simple lamina which is having a set of fibers there, so these are you can see the longitudinal fibers arranged in a matrix portion, and there will be a direction. So this is the direction 1, which is called as the fiber direction, which is also called as the longitudinal direction properties. The second direction, which is perpendicular to the fiber, which is called as the transverse direction, and we can have out of plane properties also. But usually we have a orthotropic behavior of the material, or some of the time they may behave like a transversely isotropic. So we are interested to know what is the property of this lamina in the longitudinal direction, transverse direction, and in plane shear properties. So that if you want to know how we can analyze. So that's the purpose that we should make a micromechanical modeling. Now the method that we use is called a representative volume element method. Now what we have in this method, so there is a lamina in which we take a small portion of that as a representative. Okay. Now if I fit this representative at a multiple locations over the lamina, it is going to be give you the complete geometrical shape. Then only it called as a representative volume element. If I fit all the representative in my geometry, it is going to be form my complete lamina. So it is a representative. It should be ideally a small portion and representative volume from a complete volume of your lamina. And when I took this here, it will having a certain length of my RV. There will be a certain width of RV and the certain height of the RV. So which has only one fiber at the center, and all the remaining portion in the cube is going to be a remaining portion other than this circle is going to be a matrix portion. So this is the way I make a representative is to be selected for a unidirectional lamina. Now I am going to discuss about the method that we use it for a RV problem. Now the question is how we pack it. So how the packaging of the fiber in a matrix is carried out. So if you see, this is a layer of first layer of fibers, second, third, and fourth. This is a cross-sectional view of my laminate. And in this, if I take a portion of this like this one, where at the quadrant portion, 4 corners, I have a quarter fibers, and the remaining portion is a matrix. This is also one of the way you can take the representative volume element. Second method, you take the portion like this one, in which the fiber is at the center, a complete circular fiber is at the center, and remaining portion in this square is of a matrix. This is another way. Or third way, you can take this representative like this one, diagonally, where I have the quarter fibers at the end, and also we have this fiber at the center. So out of this, right now, I have made this choice for the simply give you the idea about how this RV works. So this is type of pattern called as a square array. Okay. So what is square array? So we have a square as a representative. So length, width, and height is going to be ideally same. So whatever the length we have it, say A1, A2, and A3. All the geometrical parameters of this cube, which are taken as a representative, are same. A1 is equal to A2 is equal to A3. And in this, the corner portion, we have the fibers, 4 quarter fibers. Okay. And in between portion, which is a matrix portion, which is used to bind these fibers together. So this is a pattern that we call a square array. The second pattern we can have is a hexagonal array. So what we have a hexagonal array, instead of a consecutive, we may have an offset between the layer. So if you see the layer 1, okay, this is a layer 1 and this is a layer 2. So fibers, if you see vertically, they are not perfectly aligned. There is offset between them. So in that case, from this one layer to another layer, we go with a height, different height than the water square one. So there will be a rectangle is going to be formed, and there is a geometry by which we should know the dimensions. So here, if you are knowing the value of A1, we can calculate what should be the value of A2 and A3. Or if you are knowing the value of A2, we can calculate A1 and A3. So this is what a dependent parameters we have it. And this is a type of pattern, what we call a hexagonal array of a packaging. So you can see that there are two ways you can have the packaging of fibers in a matrix. One, square array, and second, a hexagonal array. Now question is how we should model it. So if you want to make a preparation of this RV, there are equations we should make use it. So the equation for the square array, which is very simple, that is VF is equal to A1 into pi by 4 DF square divided by 4A1 A2 A3. Now what is A1 A2 A3? These are the geometrical sizes that you have selected for this square cube. Okay, or the A1 A2 A3 are the length, width, and height of this cube. That is a simple simplification of this parameters. Whereas what is the DF is what the diameter you are expecting to model in a RV. That is what we call as the diameter of the fiber. And VF is the volume fraction of the fiber. Now what is mean by a volume fraction of fiber? volume fraction of fiber is the ratio of volume of a fiber to the volume of a composites. Because when you are going to form this cube is going to be there is a length, width and height for the cube. There is a length, radius for the fiber, there is a length for the fiber. So you can see what is the volume of one fiber. If you multiply that volume of fiber into 4, you can know what is the total volume of a fiber divided by a volume of composites. That is the size of this cube, which will give you what is the volume fraction of fiber. So how much content of fiber you want to incorporate in a matrix, that is about a volume fraction. And that is to be known because we are knowing that control of fiber in a matrix. So we are knowing the volume fraction of fiber. We are knowing the geometrical sizes of your cube, A1, A2, A3. So by solving this equation, we can calculate what should be the diameter of fiber to be used while modeling of this RV. So we can calculate the DF. And once you know the DF, the maximum volume fraction we take is 70%. Okay. The second hexagonal array, we have another set of equation. We use the same way. And again, you can calculate what should be the diameter of fiber. Use it in the model. The thing is that we are knowing with a A1 value. First, we calculate what should be the A2. So A2 is equal to 4 times of A1. A1 is your length. So that we are knowing it, say. Okay. So 4 times of that will be your A2. And A3 is A2 into tan 60. So you can calculate A1, A2, A3, use it in this equation. VF is known, geometry is known. We can calculate DF and we can model it. So this is about this one. The second step we should know is a preparation of RV is a meshing. So we have to carry out a map meshing for this type of problems. So how we can do the map meshing for this one? So map meshing will decide how many number of elements to be created on the geometry that we have prepared. So it is the more complex portion of this problem is the interface, where the fiber and matrix are the interfaces, or this is the interface where you have fiber and matrix. So we have a more number of elements on this interface, whereas we can have a very small number of elements over the length, which will save your computational time. So for base of that, we have map meshing, and we have used a solid 186 20 node element, which is a 3 DOF per node element we can use for preparation of this RV. Now the second task is what should be a boundary conditions. So the type of boundary conditions we should use is called as a periodic type of boundary conditions. Now what we can have it, as you say, the composites which the property are different in the 3 different directions. So if you have a RV to be prepared, okay, this is the RV we have it. So what is to be there? So when you have the fiber here, the property along a direction 1, property along a direction 2, and out of plane property you want to calculate. So we should apply a load in direction 1. We should apply a load in direction 2. We should apply a load in direction 3 and see how they behave. So that's why we have a 3 different load cases: load 1, 1, load 2, 2, and load 3, 3. Each load case is specified for getting a property along each of the direction. Yeah. So what we have, so for the fiber and matrix, what we have in this RV, there you have a displacement directions. So displacement U is the displacement along a direction 1, V is a displacement along direction 2, and W is the displacement along direction 3. So when you have this UV, W are the directions for the first case, that is a load 1, 1, what we have, there will be a surfaces of the cube. So what are the surface? So I will say that they are having the 1 is nothing but the X direction, 2 is nothing but the Y direction, and 3 is nothing but the Z direction. So what can I have? The back surface I will call as I will call it as say plus X and minus X. So direction 1 there will be 2 surfaces, that is plus X and minus X. Direction 2 there will be 2 surfaces, plus Y minus Y, and direction 3 there will be 2 surfaces plus Z and minus Z. So for each of the surface we have the conditions to be applied. So for the load case number 1, we put the back surface, we say the right surface will be say, so this is constrained as 1. So we allow to displace equal to of its length. Okay, so if it is having a displace its length say A1, we give a displacement should be equal to 1. Okay, so that's why. So we'll apply a same displacement. Is 1 mm is the geometry, so 1 mm will be my displacement boundary condition. And the other surface for this plus minus x, we apply 0 displacement boundary condition, and the other surfaces for x we left to displace it. Similarly, for the direction v, I will left plus x plus z minus z, and apply a plus y and minus y on these two surfaces. Okay, plus and minus surface, I put it to be a 0. And the third one, I left it plus x plus y minus y is to be displaced, and apply plus and minus z is to be constrained. So you can see that for the RVE cube, so here if you see the cube, I have a plus x, plus y, plus z minus z. So what I will do in the first case, this surface, except the plus x surface, plus y minus y, constrained in y direction, plus z minus z, constrained in the z direction, plus x allowed to displace equal to length, minus x constant in x direction. So these are the conditions we apply, and we solve it for the first load case. Similarly, we apply a second load case in which you will see that instead of applying on a plus x, I apply on a plus y boundary condition, and other will be a same. And in third load case, I apply a displacement constraint plus 1 on plus z surface, that is to be a 1, and on the rest of the surface I put it to be a 0. So this is the way we apply the boundary conditions, and once you apply the boundary conditions, we have to see the equations. So I will directly go with the final equation that we required. It is sigma alpha is equal to C alpha beta into epsilon beta. Now what we have, when you apply a unit value of a displacement or a unit value of a displacement boundary condition apply, in that case your average strain that we come, it becomes a unit value. Why this is becomes a unit value? Because you have say length is equal to 1, or a1 is a length, so displacement is a1. If equal to of length you have a displacement, change in displacement to original length, that ratio becomes a 1, and that ratio is 1 is nothing but you are having a strain value is becomes a 1. And a unit strain problem, if you have it, and we are directly knowing what is the stress induced in each of the element, then we can find out what should be the value of C alpha beta. So what is the value of this strain? Strain is unit. We can know what is the stress induced in the RVE, and from the stress induced in the RVE, we can directly calculate what should be your stiffness matrix coefficient. So important after solving the boundary conditions is to get what is this C alpha beta, or C, it is also called as CIJ matrix. That is a stiffness tensor matrix. Okay. So that's what you have to calculate. And once you calculate the CIJ matrix, then for example, if you have a transversely isotropic material, so these many number of CIJ constants you require to calculate. So how many are there? So C11, C22, C12, C23, and C6. So 5 number of constants you require to calculate. And once you know these 5 constants of a stiffness tensor, okay, then we can easily calculate the elastic property. So what is the way we can calculate the elastic property? So these are the equations which are the in terms of an elastic properties of the material from the stiffness tensor coefficients. So if you want to know what is the elastic modulus of the material in direction 1, even we can say it's the equation, we use the equation C11 minus twice C12 square divided by C22 plus C23. So what this CIJ? So these are the coefficients that we calculated here. How we calculate it? Because the strain is unique, we are knowing the stresses. So from the stresses, we can easily calculate CIJ. And those CIJ coefficients we use to calculate an elastic properties of the composite material. That is the E1 elastic properties of the material in direction 1, E2 elastic property, that is the modulus in direction 2, mu12 Poisson's ratio in a plane 1, 2, shear modulus in a plane 1, 2. And once you know E1, E2, mu12, G12, here also you can calculate a mu21, that is a minus Poisson's ratio. So these are the 5 elastic properties we can calculate. This is an example for a transversely isotropic, where we have only a 5 elastic constants. Same methodology, we can adopt it for orthotropic material, we can use it for monoclinic material, we can use it for an isotropic material. So this is all about the methodology that we can understood. Now the second one, how we can implement it. So for the implementation of this, we have make an ANSYS EPDL part program. So for example, a square array, I will show you. This is a program that we have developed or written it in an ANSYS EPDL. So this is the model RV square array, and the pulse epoxy, that is a pineapple leaf fiber epoxy. These are the set of radius inputs that I have it for this 10% weight fraction of fiber. If you want to calculate for 20, 30, and 50, you will have a different radiuses of the fiber. Then you decide what should be the size of your geometry. So I have taken RV size as to be 1 mm by 1 mm by 1 mm. So these are my A1, A2, A3 values. Then I will give input properties of the material. So elastic modulus of the fiber material, 34,500 megapascal. Poisson's ratio of a fiber, 0.2. Whereas the property of a matrix, that is a 3760 MPa, is the Young's modulus of my matrix material, that is epoxy, and the Poisson's ratio of a matrix material is 0.39. So this is a material that I have defined. Then we can have a element selection. Then we can create a geometry. This is the way you can create a geometry. Then we use the meshing commands. So meshing control, we can use it. So you can create the meshing for different map meshing. Then apply the boundary conditions. So you can see that these are the LS right one. So this is my first boundary condition, LS11, that I have explained you. So what we'll have it in this one? So I have a plus x, this is x0, and x is equal to at A2. So this is minus x surface, this is plus x surface. For both the plus x and minus x surface, I have applied a boundary condition, that is ux is equal to 0. This is y plus y, this is minus y surface. So for plus and minus y surface, I have a boundary condition, uy is equal to 0. Displacement along y is equal to 0. And when I have a z is equal to 0, that is a plus z surface, where I have put uz is equal to 0, and z a1, that is a minus z surface, I have given a displacement uz is equal to a1. So this is why the way I control the displacement of my RV, so I can get a unit strain for the first load case. And similarly, I can apply the second load step file. You can put the boundary condition, and you can write a third step boundary condition. Then important to have a stress calculation, how to calculate the stresses. So here the logic that we have to use is we calculate volume first. What is the volume of your element that we have defined? Then get the elemental stresses. So I have the 6 stresses of this element, each of the element. Then what I will do, I will calculate a stress by element volume. So I just SXV calculate, that is how we calculate SXV. For each of the volume, the stress into its volume. So I can get a stress by element volume. Yeah. And once you calculate all the stress by element volume, then I integrate the stress. Okay. So total volume, total SX, total SY. So these are the stresses for each of the element and its corresponding volume. These are the stresses. Total SX is the complete stress in your RV model. Okay. Total VOL is the total volume of your RV. Yeah, it's a sum of your complete volume of each of the element. And by calculating a total stresses, then I will calculate the average stress. So how we calculate the average stress? Total stress in x direction divided by total volume of your RV will give you SXX, that is the average stress in XX direction. Similarly, YY, ZZ. So these are the 3 normal stresses I will calculate, and these are the 3 shear stresses I will calculate from the above calculations. And once you calculate the stresses, stress vectors you calculate, then we can know that if the strain is unit and you are knowing that stress is equal to a stiffness tensor Cij, from this SXX to SZZ, we can utilize this one to getting a coefficients of Cij matrix. So we can know what is C11, C21, C31. Okay, for each of the load step, we get the corresponding coefficient. So we can calculate this Cij coefficients. Once you get the Cij coefficients, we can use the equation of Cij, which is used to calculate the longitudinal elastic modulus, and we can get the property of this. So we can calculate EL, NUL, ET, and so on.
Excuse me, sir. Excuse me, sir.
Yeah. Yeah.
Sir, time limitation. Sir, please.
Yeah.
Because other guests are waiting.
Yeah. I will end by how 5 minutes, please?
Okay, sir. Okay.
Yeah. Okay.
Thank you. Thank you.
So this is the way we can have a program, we can implement. So this is one of the last point to be discussed is about a case study that I want to discuss. So this is a material we have it, pineapple leaf fiber with epoxy. The compositions we have 8% to 50%. Okay, these are the input material properties. So this is from one of the book chapters from which I have put it. So this is the way we can have a strain counters can be generated. Okay. So this is for the stress in X, strain in X, strain in Y. This is the stress counters we can have it, stress in X and Y direction. So this is earlier was is about a square array. Now this is for hexagonal array. Okay. And important to understand the interface is modeling is important for this, which will give a more idea about the results. And these are the results, some of the results that I want to show you, that the longitudinal modulus, how it can be affected with the change in volume fraction, and the comparison of the square and hexa RV results with that of some of the analytical equations we have tried, and we can see that this modeling technique has a good agreement with for all of them. Increasing volume fraction, their property increases, and all the time they are good agreement with the analytical model. So this is the result of transfers that we have plotted, which will give you more insight on the results. So this is the in-plane Poisson's ratio. This is the shear modulus, how it is going to be changed with. So we have tried to compare the results of this micromechanical modeling technique to that of an analytical models. So this is all about my few of the case studies. Because of the time constraint, I will not discuss. Okay, but you can see the last point is the micromechanical model. So this is only for UD. You can go extend it for a interface modeling. You can go it for the woven composites modeling. You can go it for the randomly distributed spherical particle. So this is a method we can adopt for a different variety of problems to be solved. So with this note, I will end my discussions. So thank you very much for kind listening to my experience. And I wish to give a special thanks, many thanks to a core committee of ICES 2020. So all the members of this committee, I'm very thankful for giving me an opportunity to discuss with and share my experience with this. And a special thanks to Dr. Sandeep Kale sir for giving an invitation to be a part of this. So with this, I will end my session and I will stop my words over here. Thank you very much.
Thank you very much, sir, for giving the guidelines. Madam, Madam, please continue.
Okay, thank you, Yashwant Munde, sir, for providing. I really appreciate from Jai Hind College of Engineering, Kurand, for providing your valuable time and guidance. Thank you once again, Dr. Munde.
Yeah, thank you. Thank you very much. I will end my sharing of the PPT and I will unmute. Thank you. Thank you very much.
Okay, thank you, sir. Now I would like today's keynote speaker, Oyutipo Sunday Olainka. He is a professor of mechanical engineering at the Department of Mechanical Engineering, Convent University, Nigeria. He obtained the bachelor degree and master degree in mechanical engineering from the University of Ilorin, Nigeria, and University of Ibadan, Nigeria, respectively. He bagged his PhD from mechanical engineering degree from Convent University, Nigeria. His PhD research work focused on thermodynamic performance analysis of selected gas turbine power plant in Nigeria. Professor Oyutipo has over 19 years of research and teaching experience at University of Polytechnic levels. He has supervised 1 PhD students, 2 master engineering students, over 30 undergraduate projects, and 9 higher national diploma projects. Currently supervising 1 master engineering student, co-supervising 2 PhD students, and supervising 1 PhD student. He has published over 120 papers in national international journals, book chapters, and conferences. His major contribution in the area of energy system and environmental noise is the publication of research and review papers in the leading journals such as Renewable and Sustainable Energy Reviews, Energy Conservation and Management, Data in Brief, energy and power engineering, energy exploration and exploitation, environmental monitoring, assessment and Journal of Environmental Studies. The papers especially published in environmental monitoring assessment have been selected 25 hottest articles of the journals several times. So such a valuable personality is with us. His keynote speech title is Promoting Bi-Energy Utilization in Developing Countries Pathway to Sustainable Development through CDM. So I would like to Professor Oyudipo to start the session. Please, Professor Oyudipo.
Sir, yes, sir. Welcome, sir. Welcome and very good morning, sir. Over to you. Hello.
Okay, I want to share my slide.
Yes, sir. Yes. You can share your camera, video. You can share your video.
Can you see it now?
No, sir. No, sir.
Okay. Hello, okay.
Hello.
Hello? Can you?
Sir,
Hello?
yes, sir. Hello.
Can you see now?
No,
Yes.
sir. No, sir.
Not yet?
Not yet, sir.
Not yet?
No, no, sir.
Can you see now? Hello?
No, sir. No, sir. Sir, on your camera. Yes, sir. Now,
Yes.
now visible. Video visible.
Yeah, try to hop the video from your hand. Yeah. Can you see now?
No. Now share. You can share screen, sir.
Yeah. Can you see?
No, sir. Sir, can I share your presentation from here, and you can explain.
Okay, let me see. Let me see. Let me try again because I've updated something.
Okay, okay. Yes, now video is visible, sir.
Okay. Okay.
So can I share your slides from here, and you
Let me
can.
see. Okay.
Is it okay, sir? Or you want to share from your side?
I want to try from this side. Let me try again. If not, so you share for me.
Okay, okay.
Let me see. I'm coming. Can you see now? Is it okay?
No, sir. Not yet. Not yet.
No, okay. Let me. Hold on. Okay. Can you share from your hand?
Yeah, sir.
Okay.
I can share.
You can?
I can share, sir, and you can explain, sir.
Okay.
Should I share?
Yes.
Okay. Full screen. Full screen किधर है? Yes, sir. And now you can continue, sir.
Oh, I can't. It's not showing here. Sorry, it's not showing here.
Screen is visible now?
No.
No?
No.
It is visible, sir.
Okay, then let's start with here. So let's start from here.
Yeah.
Okay. I want to say good morning to everybody. Greeting from Covenant University, Nigeria, to you all. Covenant University is a Christian mission university, a private university in Nigeria, located in southwest in Nigeria. So I want to say good morning to everybody. This morning, I'm making presentation on promoting bioenergy utilization in developing countries, pathway to sustainable development through CDM. We have the outline of my presentation, preamble, why energy, global energy supply and demand, driver for energy demand in developing countries, sustainable development goals and CDM, an overview of bioenergy, driver behind development and promoting of bioenergy, sustainability issue of bioenergy. Then we move to conclusion. Then preamble, why energy? Energy serves as a foundation stone of modern industrial economy because energies provide the following services for human all over the world. Number one, for cooking and space heating, for lighting, health, food production and storage, education facility in schools, secondary school, higher institution, for mineral extraction, for industrial production and transportation, and so on. We see without energy, all these services are nowhere to be found and not be able to be achievable. Energy plays key roles in addressing major challenges of the 21st century issue, also as such as climate change, economic and social development, human well-being, and global security. So this is the area of application or the issue that energy could address even in this our 21st century, when we try to shift energy sources from conventional energy source to renewable energy. There's tendency to bring about climate change. Apart from that, there'll be economic and social development and human well-being. Energy has been identified as an essential tool to facilitate social and economic activity of any nation. So therefore, the lack of available energy service correlates closely with many challenges of sustainable development, such as poverty alleviation, advancement of women, then protection of the environment, job creation also being included among them. The energy challenge in developing nations. We see developing and emerging economic are faced with twofold energy challenge in the 21st century. Number one, the need to meet billions of people who still lack access to basic modern energy services are there. Apart from that, we see that participating in a global transition to clean, low carbon energy system. Then we look at global energy supply and demand. Global energy supply and demand. We see that presently, fossil fuel dominate the global energy supply and have been doing so since the dawn of the Industrial Revolution. Among these conventional fossil fuel, we have coal, oil, and gas. These are the major primary energy drivers globally. And since 2000, primary energy supply of coal has increased by 65%. That of oil has increased by 22% and natural gas by 50%. While at the same time, renewables has increased by 48%. So we look at the total primary energy supply globally, we can see from the figure 1. From 2016 to 2017, the supply of fossil fuel has increased more than the supply of renewable. Yes. While the 1.5% increase in total primary energy supply during 2017 has been matched by coal, while renewables are lagging behind. There have not been much contribution from that. So we see again, gross final energy consumption globally. This energy consumption globally from table 1. This can be seen that we see that the gross final energy consumption of energy sources from 370 PJ an increase of 20% over the past year. Among this one, 40% of the energy consumed globally comes from in the form of oil and oil products, while coal and gas have an equal share of 20%. Therefore, the share of renewable energy in the gross final energy consumption globally was 17.7%. There has been a drop of 0.2% over the previous year compared with that. So in this case, renewable energy sources have shown promise in meeting the energy demand globally. The exponential growth of some of the technology are promising, like solar power. This has increased 11 times, while wind energy has increased by 35 times since 2000. However, both started off from very low share, but there's improvement. But in order to make a significant contribution in reducing fossil fuel use, it is crucial to continue the rapid expansion of renewable energy technologies, and at the same time, focusing on reducing our global energy demand through energy efficiency. So again, we can see from figure 2 here, gross energy consumption in 2017. So here we can see among renewable energy sources, bioenergy, energy from biodiesel, energy from bio-based sources is the largest renewable energy source. So in 2017, bioenergy accounted for 70% of the renewable energy consumption. The contribution of bioenergy has been decreased by a few percentage annually, probably because of decreasing use of traditional biomass sources. Here we see again the gross final energy consumption in continent. Among the continents, Asia is the largest consumer of fossil fuel. So we can see there, the region consumes close to 80% of the coal produced globally, 40% of oil and oil products. This is followed by North and South Americans at 30% and Europe at 21%. The continent is also the largest consumer of renewable sources such as biomass, hydropower, wind, and geothermal. What are the drivers for energy demand in developing countries? We want to look at the driver. What are the factors responsible for the energy demand in developing countries? And we already know that an adequate energy supply has been identified as a key precursor for economic, cultural, and social development. On the other hand, energy use is regarded as the major underlying cause of greenhouse gas emission and global warming. So the bulk of the projection of the Energy Information Agency indicated that energy demand is expected to increase considerably in coming years. And this one is due to population growth and economic development. The bulk of this energy increase will take place in developing countries based on the projection that have been made. And that one will increase from 46% to 50% between 2004 and 2040 That being the projection. So energy consumption in developing countries is projected to grow at 3% per year. That's what, while that of industrialized countries is 0.9%. Among the drivers for increased energy demand in developed countries include number one, that being form of manufacturing centers are shifting toward Africa and South Asia, especially India, resulting in energy consumption growth. Not only that, natural gas and petroleum products consumption is rising in Asia faster than supply is growing, and potentially shifting trade pattern and infrastructure investment. Apart from that, we have end-use consumption is increasingly shifting toward electricity. More energy-intensive forms of consumption are expanding, such as car ownership. For example, China has become the largest passenger vehicle market in the world. Also, light vehicle sales in the developing country regions of Asia and South America are projected to grow from 42 million in 2017 to 58 million in 2024, which would represent more than half of global sales that year. Also, local businesses and industry are consuming increasing amount of energy to provide goods and services to this consumer. So, moreover, government and the public sector generally consume large amount of energy in delivering various social, commercial, and administrative services such as education and healthcare, utility-based electricity, physical administration, and security. So, all this respond for a major factor for energy demand in developing country. Then we look at sustainable development goals. How can we sustain this energy and make it available? As you already know that millions, billions of people in developing country have no access to clean and affordable energy. So we need to understand that the current pattern of energy production and use, which have shaped the development process in the past, are unsustainable. The energy challenge now faced by developing countries is to provide energy services that allow all people to achieve a decent standard of living consistent with sustainable human development. This link between energy and development remains a key factor in developing policy. So it is a worldwide acknowledge that energy consumption must be reduced in order to mitigate the climate change that constantly occurs because of it. The number are from the SDG, we have the number 7 goals. It refers to affordable and clean energy. So this goal has two sides. Number one, increasing the accessibility to electric power for the poor or isolated community. Number two is related to increasing the percentage of renewable energy source in the total consumption of energy, and even replacing the conventional energy with renewable energy production. And now, clean, reliable, and affordable modern energy services are prerequisite for achievement of the Millennium Goal. And from the CDM, Clean Development Mechanism, defined in Article 12 of the protocol, allow a country with emission reduction or emission limitation commitment under the Kyoto Protocol to implement an emission reduction project in developing countries. And therefore, CDM is an interesting instrument to release an incentive for new projects and new activities in energy efficiency and renewable. So it's a good tool, it's a good incentive way, in such a way that energy projects were able to embark on renewable energy and increase activity on energy efficiency. So therefore, why now about bioenergy? So that's aspect of thing we need to look at, and they focus on this presentation. As we know that bioenergy is one form of, is a renewable energy, and therefore is able to address the issue of climate change and even make energy available to rural dwellers in developing countries in such a way that energy can be available for them and able to have a clean.
Sir, you are not audible. Sir, voice is cut down. Hello, excuse me, sir. Hello. 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 Sunday, sir. Your voice is not audible. Voice cut down. Okay, there is a technical issue, so that we have to resolve very quickly. There is a technical problem due to some technical issue. The Sunday sir has left the meeting, so we are resolving very soon. Please be cooperate. Madam, just a minute. Let me check he is joined or not.
Hello.
Yes, sir. Sir,
Yeah.
From there the connection has been lost. So due to this problem, we have to continue with our next resource person. Madam, please continue.
First, I would like to thank Professor Oyodipo on behalf of Jai Hind College of Engineering for his valuable guidance and his valuable time. Now I would like to introduce our today's keynote speaker, Honorable N.R. Korkunde. He has graduated in mechanical engineering from Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, and post-graduation in design engineering and PhD in mechanical engineering from BITS Pilani in 2012 to 2015. He has 11 plus years of teaching work as a reviewer for more than 20 plus international reputed journals. He is life member of ISTE and SMRFRA. He had published over 62 papers in international conferences and journals. Such an eminent personality is today with us. So now I would like to request Dr. Kurkunde, please start the session.
Yeah.
Sir, very warm welcome. Sir, over to you. You can continue.
Yes. Thank you very much for briefing me, introducing me. So let me share the slides with you. So the slides are visible?
Yes, sir. Yes, sir.
Yeah.
Yeah, fully screen, sir.
Yeah. Just a minute. Good afternoon. So first of all, thank you very much for inviting me for keynote talk for ICESA 2020. I can have a strong belief that the participants will get benefited by publishing their research work and presenting the research work. So as the brief introduction is given to me, so just I will overview. I am presently working as an assistant professor in mechanical engineering department of BITS Pilani Hyderabad campus from last almost 8 to 10 years. So my talk is actually, this is my recent PhD student work which I am presenting to all of you. So the talk is based on experimental and numerical studies of deformation and worm forming behavior of nickel based super alloys for elevated temperature. So the outline I can briefly discuss because already it is delayed, so I can try to wind up everything by half an hour. So I will discuss the introduction and applications of nickel based alloys in various nuclear industries, aerospace industries, and then how do we do the forming study. Actually my research area is a formability investigation of different materials at high temperature cryogenic conditions and at the different processing routes. So how do we do the systematically the forming study, like initially the material testing and its material testing and characterization. So I will more mainly spoke on here the Inconel 718 alloy, which is a one of the extensively used alloy among the all the available nickel based alloys. And then we'll discuss some points related to material model development for using it for numerical analysis for finite element studies, and then how do we do the experimental and numerical studies on forming limit diagrams, and then finite element analysis and few conclusion and references. So coming to the introduction, just for the audience purpose, I will give the brief introduction. There are variety of components, especially the exterior component of an automobiles, aerospace, nuclear industry, wall, and the different sectors people used to produce by using sheet metal forming process, because it is an ideal candidate which we can replace to the existing welding and machining, and the integral approach means the one component we can easily produce by using the different sheet metal forming processes. So at the laboratory level, as a researcher, we used to be tested the different material for its formability by using deep drawing test. This is the just the overview and the schematic of circular, cylindrical, or the square shaped components, conical components, which we can easily produce by using deep drawing process. Then we have a stretch forming process. Usually the stretch forming process we used when we have a dome kind of an, or we can say the spherical shapes, and usually this is a pure biaxial mode where we can assess very easily the forming behavior or the formability limit of any material. So this is a very unique way of testing any kind of a material to assess or evaluate its formability. Now there are we can say the rolling process, which we can form a different kinds of and rolled components, roll shapes, like we have a thin wall structures like a roofs and everything we used to make it by using the rolling process. Now there are many places we used to have the bending operation. There are variety of bending operation, like we can do the V bending, U bending, L bending, edge bending. So this kind of an operation as per the requirement of the manufacturing firm or the industry or particular component we need to use it. Then we have a spinning process when we used to produce a very large hollow components by using a sheet. This is a very traditional process of a spinning process we use by the mandrel and tool, and by using our conventional lathe we can able to produce a hollow components of a different shape. Then we have a incremental forming, which is a localized deformation process without using any die, or it is the main benefit of the incremental forming processes. It is a die-less process. By just a localized deformation of a point tool, we can use like a CNC milling machine and anything to produce the particular shape. So any kind of a spherical, conical shape, we can say the pyramidal shape, anything can be possibly formed by using the incremental forming. Now, we say our research area, we used to mainly focus on deep drawing and stretch forming behavior of an inconel 718 alloy, and this works is belongs to my DST project, early career research grant, which is going to be completed soon. So we used to evaluate the formability. Formability can be evaluated in a different way. The popular way is, one way is called as a limiting draw ratio. Limiting draw ratio means how much maximum initial blank diameter we can able to draw it divided by punch diameter. That is usually called as a LDR. So LDR will define what is the stretchability or the formability or the drawability limit of an particular material. Based on that, industry will decide the parameters and the stamping depth for the different components. Then usually the one of the crucial parameters in sheet metal forming is thickness distribution of an form component, because thickness variation should be minimum. It should not be too much excessively localized deform the component that will cause a unnecessary excessive stress concentration at the different region, and the component may get fail in an actual environment. So we have to be controlled very precisely the thickness distribution. That is one of the challenge of having the formability test. Then we have one kind of an error or the accessibility called as a airing. This kind of a zigzag shape. If you see the top view not exactly the circle. So if I want to use this particular component, I have to cut it somewhere from the down to use it. So this is an unnecessary called as a defect or the wastage of a material that need to be minimized it. And this usually happen because of an anisotropy present in the material, because usually we use the sheet material. Sheets are produced by using the different kinds of an rolling processes. So because of an rolling, the grains will get oriented in one particular direction. So usually the material properties are superior in that one particular direction. So that will cause a uneven distribution of an material or the material flow when you draw it, and that will create a airing tendency. So usually the formability can be assessed or evaluated or can be controlled by using LDR, thickness distribution, and airing. Similarly, we have a wrinkling tendency, means the folding of sheet on each other. So the folding may be caused because of many things, because of an excessive spring back, because of an excessive blank holding force. These are the some reasons which may create such kind of foldings on a sheet, which is an undesirable effect usually that need to be reduced it. Similarly, if you go for the stretch forming, we can able to, like a LDR, we can able to know or understand the limiting dome height of a material, which will also define the stretchability limit or the drawability limit of an material. Similarly, here also we can able to draw the thickness distribution, and the one unique characteristic where the industry or the researcher are extensively using everywhere is called as a forming limit curve. So the forming limit curve will define us or understand us what is the limit of an forming for a particular material. So usually for the traditional stretching of any material, will get the forming limit diagram like this line. The solid dark line which you are seeing in this diagram is called as a forming limit curve, which are plotted again major strain versus minor strain. Open surface strain, if you able to measure it on a form component at a different region, because we have to do the test at uniaxial test condition, plane strain condition, biaxial condition to get all this continuous line. So below this line is usually called as a safe limit, and above this line is material is unable to form it. So material get tear off, material get fracture. So any kind of a failure may happen above this line. So for the researcher or for the industrial point of view, it is very essential to understand and analyze exactly the FLC line. FLC line will talk, will able to know that how much we can able to form this material. Means usually if you stamp form the component, we should know what is the depth we can assure that without any substantial thickness depression, without any cracking, without any fracture, we can able to form the component. So we used to study this different shape forming limit curves and how do you plot it. So usually all the nicking points we used to draw this forming limit curve. So for the shaper side, like we know everyone like factor of safety concern. So we used to have a shape forming limit slightly below than the forming limit curve. Let us say 5 to 10%. So that we can make sure industry or those who are using the component in an actual environment that you can try to form the component below this line so that it can be safe everywhere to utilize it. That is usually called as a safe forming limit. As I mentioned, the wrinkling is a serious issue in all the stretch component or the sheet, because these are all thin sheets in the size of 1 millimeter, 1.5 millimeter or 2 millimeter maximum. So it has a tendency to fold it or wrinkle it at many places. So we need to determine the wrinkling limits also by using this diagram. So usually the wrinkling tendency is usually happen in case of an uniaxial region. The left side part of the vertical arrow, if you are seeing here, the left side part shows a uniaxial region, right side part is usually shows as a biaxial region, and this vertical line is usually under a plane strain condition. And then obviously the fracture used to be substantially above than the nicking tendency. So in some cases, especially when we used to do the incremental forming metal spinning, you will not get this traditional FLC curve. We used to have a forming fracture limit diagram because all the fractures will happen in a plane strain condition. So you will get a straight line, especially all the high strength material where the ductility is limited and substantial nicking tendency is not there, like a for example, if you see the inconel alloys and you can say the titanium alloys in such kind of an high strength alloys, you will never get the FLC, traditional FLC like the other material. So we used to go with the FFLC. So this is a overall basic introduction of an forming limit diagram. So I will focus now onward on FLC. So usually the FLC we used to plot by using a ASTM standard, and sometimes it is a ISO standard and ASTM standard, both are similar, there is no any much change. So the ISO standard 12004 we used to follow to do the Nakajima test. So the specimens, usually the minimum number of an specimen we used to do the Nakajima test is 6. 1 to 3 specimens are for the right side of the FLD. If you go previously this right side of an FLD points, we can get it by using 1 to 3, and the left side of the points we are getting with using this. So if you see that we are reducing the width of an component, if you are reducing the width, this is the 6 number component, indicate that it is in pure planes, pure uniaxial region. So if you are keep on increasing the width of an specimen, this 4th and 3rd point belong to plane strain, and the 2nd and 1 point is belong to biaxial region. So the different kind of an stretching like biaxial stretching, plane strain stretching, uniaxial stretching we used to do with the Nakajima test. And as I mentioned, there are numerous applications of sheet metal components, especially for this inconel alloys that are extensively used in the sports cars, automobile parts, aerospace application, cryogenic tanks, gas turbine engine parts, marine application, off-field castings, domestic application like washing machine. Many components are made by using nickel-based alloys, beverage cans, turbo pumps and seals, and there are many applications which are produced by metal forming applications. So the major challenge of this high strength alloys is it has very limited ductility. So usually one of the basic requirement for any kind of a metal forming process is it should have a high ductility so that material can flow very easily and the desired shape can be formed. But the major challenge will come when you have the limited ductility. Let us say the the titanium alloys, it has very limited ductility. Let us say at room temperature it has only less than 10%. So sudden fracture you will realize if you start forming the component at a room temperature condition. So one of the alternative to overcome such kind of a limited formability issue is heating up the material or forming at elevated temperature. So forming at elevated temperature is what you say, the recent research area where the researcher are focusing on how do material behave, what is the formability evaluation of a different material at an elevated temperature. So this my DST project is also related to the formability of an nickel based superalloys at elevated temperature. So we have studied up to 800 degree how the material will affect the formability and what are the complex shapes and component can be formed at elevated temperature. So this is the methodology we have worked on my PhD student. So initially we have determined it is very essential to determine the or understand the deformation behavior and the material properties of any material before you start doing the formability study. So initially we have to do very thoroughly the material property determination and flow stress deterioration, and then based on that we have to build the models, we have to build the anisotropic yield criteria, then we have to do the formability study, and then that will go as an input for the AFE simulations, and then that can be validated with forming, fracture and wrinkling limit diagram. So material testing and characterization. So obviously the very popularly used uniaxial tensile test will used to do the tensile test at different temperature. So the material is very costly, so we usually prefer the sub-size ASTM standard specimen, which is exactly 50% reduction of an original one to test the specimen. So this is a schematic of an dog bone specimen, tensile test specimen of an thin sheet of an 1 millimeter thickness. So these specimens will used to test the material properties at different orientation. As I mentioned, sheet is very highly anisotropic, so it is very essential to test the material properties at different rolling directions. So usually the 0 degree consider as a rolling direction of a sheet. Then at least minimally we have to test at 3 different conditions: 0 degree, 45 degree and 90 degree orientation. Like this, if you see the schematic, this is a rolling direction, this is diagonal to rolling directions, and this is a transfer direction to understand the material properties variation at different directions. And then we used to test it at different temperature and strain rate. Usually if you see our traditional tensile test machine, we used to conduct the constant speed, but for the sheet metal application we'll usually prefer at constant strain rate. Constant strain rate is a different phenomena. The increment of an strain with respect to time is a constant, means the increment of an strain value should be constant, not the speed. So usually the speed used to be very exponentially. So the sophisticated special purpose uniaxial machine which have this kind of an arrangement should be used to test it, because all the models or material models are based on the input of strain rate, strain and temperature. So we have tested the Inconel 718 at room temperature to 700 degree at an interval of 100 degree with the 4 different slow strain rates. Strain rate ranges are given here. Usually all the metal forming application, the sheet metal forming application, we used to do at very slow speed. Therefore we have to test the material in the replica of an actual environment. Therefore we used to prefer the slower strain rate. Only the incremental forming, metal spinning, these are the 2 processes which are required at higher strain rate. So you can see that there are room temperature to 700 degree means 8 different temperatures, 4 strain rates. So 8 into 36, 8 into 4, 36 test at one particular direction. So 36 into 3. So we have tested the material and repeated for thrice. So almost more than 300 plus tensile test experiment we have conducted on the Inconel material. So it will take around 1 month or 2 months continuous dedicated effort to test the tensile test material, because if you go at high temperature complication or the ductility will improve, test will take more time. Let us say for Inconel material this 0.0001 second inverse tensile test will take almost 22 to 24 hours for one specimen. So you can imagine we have almost tested 110 around tensile test specimen to make sure that accurate and trustworthy material properties. And we have used our 2-zone split furnace Bismade, which is an Indian made very sophisticated tensile test machine with contact type extensometer, because extensometer is very essential to capture the true values of stress strain. We don't want engineering stress versus engineering strain here. We want a true deformation for the sheet metal forming application to understand the real time behavior of a material. So we used to have the extensometer while testing it, and this is the heating cycle we used. Like heating rate is 20 degree per minute, and then holding time for some minute to assure a uniform temperature throughout the specimen, and then we used to conduct the test, and then we used to air cool it. We can vary this like a water cooling or the some coolant cooling or open environment, or the there are different kinds of open cooling. If we want to see the effect of heat treatment on a specimen, that also can be done at our machine. Now this is an overall schematic of an true stress versus true strain diagram at different possible combination. Just I am representing the few figures. Actually there are a lot of graphs. So if you see, for easy demarcation, we have represented at room temperature 200, 400, 600 and 700 different temperature. Then this is a different strain rate at one particular room temperature at 400 degree. Then at slow strain rate at different temperature. Then at 600 degree with different strain rate. So if you see here, obviously as temperature increases, the flow stress or the deformation or the true stress strain or the material properties usually decrease. It means yield strength, ultimate strength used to be degraded, percentage elongation will get increased. If you see here, the effect of variation of an strain rate are negligible compared with the effect of temperature. So means the strain rate sensitivity, which is a very crucial parameter in case of an metal forming application, is minimum in case of an inconel alloy. Means we should not bother about the punch speed much. So if you see here, you can find it out some serrations. That serration is usually called as a dynamic strain aging. It is called as a dynamic strain aging, which is a very adverse effect on the material, which can be found at some particular strain rate and temperature, in which the material will start behave like a combination of ductile and brittle fracture. So it can be characterized in a different way. We have characterized this. There are different types of an DSA. So usually in the inconel alloy, we used to find there is a class of A plus B type of an flow stress serration, because usually the material will resist to deform it at some location. Some location it will offer easiness that will create a serrations in a material. So exact pinpointed deformation behavior, pinpointed material properties are become difficult to get it, and material will behave as I mentioned. It is a combination of ductile plus brittle failure, which are not desirable effect. So unfortunately it has found in inconel material, usually from we have found it from 400 degree above to 700 degree at a different temperature. Then we have characterized this. These are the average material properties. We have tested at 3 times and average has been taken with the percentage variation, and the important material properties which usually required to further analyze, we have calculated it, like yield strength, ultimate strength, percentage elongation, strain rate sensitivity. If you see, strain rate sensitivity is very negligible in case of an inconel alloys. Then we have calculated the anisotropy index, which is usually called as a Langford coefficient, which is very essential to calculate in case of an metal forming, because we cannot use our traditional von Mises or the maximum shear stress criterion for the study of an sheet metal problem, because it is a highly anisotropy nature. And in order to calculate the anisotropy behavior, we should calculate the Langford coefficient. So Langford coefficient at R0, R45, R90 we have calculated. Here we have represented only R0, and then based on that we used to calculate the normal anisotropy and planar anisotropy. Normal anisotropy, if it is a good, means it has a good material for the formability, but unfortunately if you see here, the all values are around 1 or less than 1, means it has a poor formability, means it has a more challenge to form it. Planar anisotropy will indicate the airing tendency in a material, which is a low, means it has a low airing tendency. We should not worry much about the airing tendency. And strain hardening exponent is usually the difference between the ultimate and yield point divided by 2. So if it is value is more than 1, so it has a good hardenability capability, means the component is more tougher and high strength when you produce it. So that is a better advantage you have compared with the other traditional material. So this is the way we calculate the planar and normal anisotropy and other parameters. So then we have used, we should understand, because strain hardening is one of the crucial parameter, and we should know what kind of an hardening mechanism that material is behaving. So we have used the different flow relations like Holmol equation, Swift equation, and Ludwig and Vosan. So I'm not going in depth because it will take long time to explain it. So these are the equation we used, and we have plotted the deformation behavior and the phases, and we realize it is a two-stage hardening. This has a two-stage hardening. So so the deformation behavior is slightly more complicated, and we have seen that the Bose will be perfectly suited to predict the deformation behavior of a material. These are the different stages. So we have plotted the instantaneous strain hardening rate versus net flow rate, and we realize that the deformation in the material usually happen at third stage, fourth stage, and five stage. Usually for any material there are 5 stages of an deformation. So usually this material used to follow from the third stage, fourth stage, and 5 stage of an deformation. Then we have done the factography study, specimens specimen of an tensile test broken specimen in a thickness direction. We have taken as a sample for the factography, and we realize that there is a mixed granular fracture which having a some flat region as well as dimples. Dimples indicate a ductile failure, flat region indicate a brittle failure, which also confirm a DSA region here. And some voids are there, some of the carbide particles are there. Their compositions we have tested by using XRD EDX. That detail I am not presenting here. Then based on this input data, we have presented a constitutive model. Constitutive model is basically the mathematical description of an flow stress behavior, which can be used as an input in a numerical simulations and finite element simulations. So basically it is classified into a 3 different way: the phenological constitutive models, physical based, and artificial neural network. Phenological constitutive model is nothing but the curve fitting. Based on the input and output, and based on the curve fitting mechanism, you will get the constant. So it is missing a physical sense, but it can be valid over for a one particular material, but it is not valid for the longer domain. But physical constitutive models are depend on the physics. It has a proper base, like it is based on the activation energy, then the slip systems and everything. So it is a more realistic and more, what you say, the larger domain we can implement the physical constitutive model. Again, the ANN is also a one tool which can be used to predict based on the input and output trend. We can able to predict the flow stress behavior. So we have tested for this material at very different mechanisms or the very different constitutive model which are available in the literature, like a Cooper-Salmon, Johnson-Cook is very popular. These are the many models. You can find it out in the popular finite element softwares like the ANSYS, Celestina, Abacus. So this constant need to be calculated and give as an input for FE simulation. We have tested Cooper-Salmon, Johnson-Cook, Zerial Armstrong, modify Johnson-Cook, modify ZA, integrated JCZA, Arrhenius, KHL model. So I'm not going in depth how we have calculated the constant. We used to write the MATLAB code for this, and after a regress input data of an 1110 experiment on a tensile test, what we have done, the plastic data we have give as an input here. This is a non-linear code which can be run in a MATLAB, and we use to get the constant. So I'm skipping how we have calculated it and what are the steps are available. And these are the material constant for Inconel 718. We have tested from room temperature to 700 degree at different slow strain rate, and this will become as a act as an input for the different numerical simulations. So these are the comparison of flow stress graph. This is a 3D diagram we have plotted. This diagram, if you see here, it has been plotted true stress, strain rate, and temperature and strain values. So usually the best predicted model can be calculated based on correlation coefficient, its average absolute error, and standard deviation. These are the 3 statistical parameters we'll use to calculate the suitability of the model for particular material. So we have calculated that, and we realize this R value is nothing but the correlation coefficient. We use this equation to calculate it, the average relative error and its standard deviation we used to calculate. Sometime even though the R value is higher, it will mislead or misbias, because we cannot define how much it is positive side and negative side. Therefore, we used to calculate the average error also and its standard deviation. So if you see here, the best suitable models are JCZA and KHL, which having a higher correlation coefficient, the lower average error. So we have found that for the Inconel 718 material, the JCZA model is a best suited model, which we can use for the numerical analysis and finite element simulation. Then, as I mentioned, we cannot use the von Mises and the Truscott-Seal criteria for the sheet metal forming applications. It has limitation because isotropy is a condition based on that this model has been developed. So we have used the anisotropic yield criteria. We consider Hill-based anisotropic yield criteria. These are the equations for that, and we have used. These are the constant which we have calculated at the different condition. I have represented here at only 3 cases: room temperature, 300 and 500, and these are the yield locus and the experimental point, which can indicate that it is very well predicted the material behavior or the anisotropy. Similarly, we have developed the Ballard 89 yield criteria, which is these are the constant, it also predicting very well. And then we have developed the KHL model also. So these are the 3 models. If you compare, then Hill extension also we have developed. So overall, by comparison of all models, we realize that the Hill extension fits very well, because this also we need to check it, the yield stress variation with respect to rolling direction and the anisotropy coefficient variation with respect to the rolling direction. So based on that, we realize that the Hill extension is an best anisotropic yield criteria, which we can use for the numerical studies of an sheet metal forming application. Then we come back to the FLD experiment. We use this warm stretch forming setup to draw the FLDs. These are the specimen we use. These are the standard specimen which we deform at the different temperature region, and these are the FFLD, fracture based FLDs. These are the FLDs, and that can be corrected. The bending strain effect can be corrected by using bending correction stress, which are shown here. So this is the experimental FLDs which we have drawn it, and that need to be validated using the numerical simulation. So we have used MK model, which are very extensively used tool to determine the FLDs theoretically, so that rigorous experiments need not to be conducted. So we have conducted the MK model. The input for the MK model is a constitutive models and yield criteria, whatever we have developed. So almost we have developed 7-8 constitutive models and 4 yield criteria. So this combination input we have given here for the FLDs for the predictions, and based on that we realize that the Hill extension with JCZA model predicts the forming limit very well for Inconel 718 material. Then we have used BW model to determine the FFLD, fracture based FLD, because MK model will not be suitable properly to determine the fracture forming limit diagram. So we need to calculate the stress triaxiality and effective plastic strain equation. So we use this equation to calculate the effective plastic strain. Stress triaxiality eta can be calculated based on the actual failure strain in the material. So here we can see that we have used the different fracture models, and we realize that the BW model suit very well. So this is overall the glimpse of our work. We have done many numerical study. My major work focus is on numerical analysis of metal forming. So how we can able to reduce the actual experimentation, and we can give the handy input to the industry in the form of an FE codes, in the form of an numerical codes, so that industry can just give the input and see what is the forming limit, how much they can at what depth they can form the component. So we have done very good industrial projects with Mercedes-Benz, and then with John Deere's also recently from Pune, as well as from the Tube India Limited. And we used to develop the handy MATLAB codes so that industry can just give the input material properties for one particular material, and they can get the forming limits of a material. Based on that, they can decide the stamping height of any component. So we have very close and strong collaboration with the Mercedes-Benz. With here we have set up the labs also. So we are testing many real-time components also. Recently we have tested the the Mercedes-Benz car door shape for the sheet metal forming, and we have successfully delivered the prototype also. So this is my PhD student work. She has come, she is going to complete it soon. So we have some part is having the objections from the Mercedes to present it in the open environment. So we have not put the real-time component which we have tested. Just I have viewed the brief overall analysis what we have done. So these are the few conclusions for the inconel alloys. One major finding is unfortunately the DSA behavior, this material is showing from 400 degree to say 700 degree. It also shows the two-stage hardening behavior with Wohs empirical election suit very well. Then fracture surface, the fracture behavior is a combination of ductile to brittle fracture. Then we have found that the JCZA model suits very well for the prediction of an flow stress behavior of an material. We have seen that Hill extended criteria also very well suit for this material. Then we have plotted the experimental FLD. We realize that there is a difficult to identify the nicking points for this material. So we have went through the fracture limit diagrams, and then we have successfully implemented the MK models. We have handed over the codes to the Mercedes-Benz and the DST also, which we have developed. So it can be easily predict for inconel material any kind of stamping applications. The numerical simulations can easily predict the behavior of a material, and they can tell whether it is formable or not, what temperature, what strain rate, and what condition they can form it, so that better quality of a component can be produced. So I am sincerely express my gratitude towards the Engineering Science and Research Board, SARB, Government of India, for providing the financial support for this work. We have taken some additional support from the Mercedes-Benz also to execute some of the experiments. I have used some of the important references to make this presentation. And almost the outcome of this DST work is we have published around 10 international journals and 5 to 6 conferences based on this work. So at the end, I would like to thank you, the organizing core committee for ICEEC 2020, especially Sri Tatesaheb Gunjal, founder president of NJCEI, then Vijay Gunjal, founder president of GCEI, Professor SD Gunjal, director, Professor DS Gule, CEO of NJCEI, and the conference chair, Professor DJ Garkal, principal, Jai Hind College of Engineering. Thank you very much for giving me an opportunity to interact with you, and I hope this conference will give a strong platform to the researcher to interact their research and take the outcome and the strong collaboration in a future with each other. So you can ask the questions related to this topic to me. You can write a email if you want to pursue the your research work in that domain. So I will hand over to the core committee for question and answer and other discussion. Thank you.
Thank you, sir. Madam.
Thank you, Dr. N.R. Korkunde, for the motivational talk and providing valuable time and keynote guidance. Thank you, sir.
Yeah, thank you. Thank you very much. Shall I log out, or do you have any question, participants?
No question, sir.
Okay, thank you.
Sunday, sir, do you want to present the remaining? Dr. Sunday, sir. Can you hear me?
Can hear you.
Yeah, so sir, do you want to continue the remaining parts?
Yes, yes.
Okay, so I'm sharing the screen. You can continue from there. Yes, sir. Now continue.
Okay. Good morning. Please not there. Can you move from the first slide? Okay. Thank you very much. So I want to continue from where I stopped other time. So looking at the overview of bioenergy.
Yes, sir. Continue.
Okay, I can continue.
Yes, sir.
Okay, thank you. So as you said earlier, that bioenergy is a renewable energy source and refer to energy derivable from source of plant origin, such as tree. And as an energy resource, biomass may be used as solid fuel or converted via a variety of technology to liquid or gaseous form. Bioenergy is presently making an important contribution to meeting global energy demand. And bioenergy can play a role in addressing energy access challenges, provide opportunity for social and economic development in agricultural communities, contribute to local energy security, improve the management of resources and waste, and provide greenhouse gas saving and other environmental issues. So here we have the total primary energy supply of renewable. So we can see from the figure 3 here, bioenergy is the largest renewable energy source globally. In 2017, the total primary energy supplied by biomass was 55.6 EJ. With the increased use of modern biomass solutions like wood pellet, biogas, and liquid biofuel, contribution of modern bioenergy sources will be a major part in the future. Again, we have total primary energy supply of renewable in continent. So we have periods from the continent we have looked at here. We can see that 96% of all renewable energy supply in Africa is contributed by biomass. It has significantly higher share in America, about 56%, Asia, 65%, and Europe, 59%. The availability of variety of feedstock to produce useful end products for use in heat and transportation benefit bioenergy development around the world. What are the favorite feedstock for bioenergy? Where this one include municipal and industrial waste, primary solid biofuel, biogas, and liquid biofuel. So we have under this one the feedstock of bioenergy being disputed as at in 2017, 55.6 EJ of biomass was utilized for energy purposes, in which 86% of the use was in the form of primary solid biofuel, and 7% of the biomass was used as liquid biofuel. Biogas, municipal waste, industrial waste had almost equal share, 2 to 3%. And we can see from figure 4 here, domestic supply of biomass in continent. So among continent, domestic supply of biomass is highest in Asia, followed by Africa and America. So both Asia and Africa account for high share of biomass due to the extensive use of firewood and charcoal. For liquid biofuel, America, USA, and Brazil had the highest share due to high production of bioethanol from corn and sugarcane, respectively. So we have potential of bioenergy production. So from table 5, data show that utilizing the residue from all major crops for energy can generate approximately 4.3 billion tons to 9.4 billion tons annually around the world. So therefore, utilizing standard energy conversion factor for residue by conservative moisture content and energy content of fuel, the theoretical energy potential from residue can be in the range of 17.8 to 82.8 EJ. The major contribution will be from cereals, maize, rice, and wheat. So in comparison, the domestic supply of biomass for energy in 2017 was about 55.6. So therefore, the total energy supply of all energy sources, including fossil fuel, was about 595 in 2017. So in other words, energy generation from agricultural residues could meet about 3 to 14% of the total energy supply. So considering all sustainable factors, agricultural residues have great potential to be part of future energy mix. Then we look at energy conversion technologies. We have various technologies for the conversion of biomass, but in order to get useful energy for heat, for electricity, or transport biofuel. We have the figure below. It shows bioenergy conversion technology. Please, are you hearing me?
Yeah, sir.
Okay. So we have the various feedstock that have been listed on the left-hand side here. We have the conversion route. Then we have the one produce heat or power or liquid fuel. So we can see from the oil crops like rape, sunflower, waste oil. So this one can be converted through combustion in order to get useful final product, or esterification or hydrogenation. Sugar and starch crop or residues can be converted through hydrolysis or fermentation, and that one be able to yield liquid fuel for heat or power. We have wood, biomass wood also can be converted through hydrolysis, through gasification, through pyrolysis, or secondary process, and that one also able to produce heat or power liquid fuel. Then we have biodegradable municipal solid waste. Also, this one can be converted by hydrolysis, gasification, pyrolysis, and then able to generate heat or power or liquid fuel. So while we have the last one, photosynthetic microorganism, so that is something like microalgae or bacteria. This one can be converted through biophysicochemical routes, and that one can generate gaseous form like hydrogen, like biomethane. So we can see the potential and the easy advanced technology for the conversion in order to keep our environment clean and make it the energy to be sustainable. So bioenergy contribution to world total energy. Bioenergy provide about 10% of the world total primary energy supply as at 2005, but in 2007, this has increased to 17.7%. And therefore, bioenergy accounted for 70% of this renewable energy consumption. While in the transport sector, the share of biofuel in 2017 was about 3%, with a total contribution of 3.5 heating. So biomass dominate the end use of sector of direct heating. In 2017, 40% of biomass was consumed in end use sectors of residential, commercial, agriculture for heating and cooking purposes, which account for about 95%. In 2017, we again biomass about 55.6 EJ of biomass was utilized for energy purposes. 86% of this was in the form of primary solid fuel, including wood chips, wood pellets, fuel wood for cooking and eating. While 7% of the biomass was used as liquid biofuel. So in this one is obtained from municipal waste, industrial waste, at most about 2 to 3%. What are the drivers behind development and promoting bioenergy utilization? So we heard there are 4 key factors to be considered. Number one, rising prices for fossil fuel, in particular oil prices. We could see that in all over the world, there's increase in price of fossil fuel. So therefore, this now giving room for promoting bioenergy utilization, especially in developing countries. And because of energy security as well. We know that fossil fuel is limited, and therefore it can be exhausted. So therefore, in order to have sustainable development and sustainable energy in the future, so therefore they need to promote bioenergy. Then climate change, the effect of climate change is another factor, and in order to prevent to reduce the effect of climate change due to fossil fuel, back on promotion of energy. Then rural development, it can provide job, reduce poverty in rural area. So therefore, it's very, very important at this point in time to promote bioenergy in developing country. We look at sustainability issues on bioenergy in developing country. Already know that energy is a fundamental input to economic activity. However, a major transformation is required in the way we produce, we deliver, and consume energy. So the current energy system is likely dependent on fossil fuel, which negatively impact air quality and contribute significantly to carbon emission. So therefore, when considering energy alternative, there are three main aspects that comes into play. Number one, economic competitiveness. So in that case, we need to look at the cost. Though when we look at the renewable energy source, the technology at the beginning may be high, but with the when we look at fossil fuel, though we see that it's available all over, but in order to make it economic competitive, there's need for the government to come in such a way that to make this bioenergy to be more economic competitive with fossil fuel. Then in an aspect of energy security is what to be considered, and the environmental impact is very, very essential. Then how they can developing country with abundant resources switch to a sustainable energy future? Number one, two critical factors are to be considered. Financing mechanism is very, very important because of the impact of costs at the initial state of bioenergy technology. So therefore, high financial input is what have been limiting the promotion of renewable energy, especially in developing countries. But if government can come in and support and bring in more investors in this area, this one can be easily be tackled. Then the other one is further technology development, because the technological development is very low. The awareness is very low, especially in developing countries. So therefore, there is need for more to create more awareness. So there will be this will be required to make clean energy system economically competitive with traditional fossil fuel. Financial mechanism allow for a reduction in some market barrier for new clean energy technology. Barrier for new clean energy technology by providing investors with less risk and uncertainty when competing with traditional energy sources. Then what are the benefits and barriers to bioenergy utilization? One of the primary benefits of bioenergy is availability in all regions of the developing country. So we see that bioenergy resources is available. They are available everywhere. So that's one of the benefits of the why they need to promote bioenergy utilization in developing country. And biomass in the form of forest product and agricultural crop along with residue is available in almost every country around the world. The use of local available resources for eating provide much needed alternative to imported fossil fuel. So among the benefits to derive from bioenergy utilization in developed world include number one, bioenergy project can contribute directly to number one, poverty alleviation by helping to meet basic needs. Number two, creating opportunity for improved productivity and better livelihood, and preserving the natural environment on which the poor people depend, especially in rural areas. So when we embark on this bioenergy, it will preserve the natural environment, which the process of production of fossil fuel has already battered. But with this one, natural environment can be preserved. Then the benefit again, we look at the following are barriers. The barriers against bioenergy utilization in developing countries. Number one, policy and regulatory barrier. In most developing countries, the policy by government does not favor promotion of bioenergy utilization. And this one had to be removed. Low level of awareness of benefit accrue from bioenergy technology conversion. So this is another challenge. The awareness is very, very low. So government need to come in and they allow more researchers to embark on the production of bioenergy. Technological and technical inadequacy is another thing. The technical aspect of producing bioenergy product is very, very low. So the technology is not yet developed. So therefore, there is need for development of technology there. Insufficient funding is another thing. low conventional energy prices due to government subsidies. So that's why also have made people to look down on bioenergy products in such a way that they are not having interest in developing or utilizing bioenergy products in developing countries. So we see that promoting utilization of bioenergy for sustainable development, we can see from this figure the connection between biomass energy system and leakage to sustainable human development. So we see biomass production through biomass conversion, as we already discussed earlier, in generating electricity fuel cogeneration. So we can see the energy services that provide, like running water, lighting, cooking, housing, cooling, and all these are being provided through this biomass production. So the impact on the economy, we see that it has great part in the economy. It improves the GDP of a country when the such country embark on it. Equity as well, accessibility to energy will be there, both the poor, people living in rural area and urban area. Social structure, empowerment, and environmental impact. This one will be reduced. So when we look at this one together, these are the factors linked to sustainable development. So therefore, promoting utilization of bioenergy for sustainable development in developing countries, this is the aim of this particular presentation, to realize the potential of bioenergy for sustainable development in developing countries. So, and this is based on two premises. Number one, bioenergy is that to be noted that bioenergy is an important part of today's imperfect energy system. Though we have talked about the benefit of it, the advantage of it, but is that on its own side, it has its own challenge. Apart from that, modernized bioenergy system, if appropriately designed and implemented, have great promise for contribute to future sustainable development. That's the most important thing to consider here. Then, for comprehensive and sustainable production and utilization of bioenergy in domestic and commercial purpose, the following recommendations should be considered. Number one, in order for us to have policy to promote utilization of bioenergy for sustainable development in developing countries, massive awareness campaign should be undertaken in all developing countries in order to populate the use of biogas. Apart from that, credit and financial incentives should be enhanced and expanded by governmental agents to farmers of energy crops like jatropha, sugarcane, and rapeseed. Then, domestic and industrialized development of ferrous biogas digesters should be considered using ferrous feedstocks. Then, law prohibiting indiscriminate cutting of trees for firewood should be enacted and courageously implemented. So this one will preserve our forests, and the wood that being used for bioenergy will be preserved. A well-structured programs and policies are to be put in place by government to work clean, dependable, and affordable electricity generation. Another one is that government to commit resources toward research and development, capacity building, and technical support for biofuel sector development in developing countries. Government of developing countries to establish regulatory and institutional frameworks that provide space and incentive for a wider stakeholder participation in development of the biofuel industry, involving farmer, academics, public and private sector institutions, investors, and non-state actors to be considered. So in conclusion, in this presentation, bioenergy resources currently available in developing countries, they are in large quantity, and the potential to utilize them for production of various type of biofuel have been considered. And we have already seen that there is potential for bioenergy production in developing countries, and therefore there need to educate people and create awareness concerning the use of bioenergy in developing countries. So in this regard, to promote utilization of bioenergy in developing countries, the government should be more conscientious for overcoming technical, political, and commercial barriers, monitoring and fast implementation of projects, providing funds, reducing costs, raising mass awareness, and research. So this is the major focus of this particular discussion. I'm believing that through this, we see that there will be more, the promotion of bioenergy in developing countries will increase, and that case, people will be able to appreciate it. So on this note, I want to appreciate the core committee of ICES 2020 for the privilege given to me to be part of this conference, most especially We have Honorable Sri Tatya Seb Gunja, the founder, president, and then Honorable Sri Fijeri, the founder, president, Professor S.D. Gunja, director, and Professor S.D. Gahi, the Chief Executive Officer. We appreciate you, and the conference chair. I appreciate you for the privilege given to me to be part of this conference. I say thank you very much. God bless you all.
Thank you, sir. Thanks
sir.
a lot, sir.
Yes,
Thank you, Professor Oyodipo. On behalf of Jai Hind College of Engineering, I am really thankful for your valuable guidance with motivational talk. Thank you once again.
Thank you, sir. Thank you very much. God bless you.
Okay, sir. So,
now it's a time of vote of thanks. First, I am very hearty vote of thanks to our today's keynote speaker of International Conference on Efficient Engineering System 2020, Dr. A.K. Sarkar, Dr. Y.S. Munde, Dr. Oyodipo Sunday Olainka, and Dr. N.R. Kotkunde to provide the keynotes with motivational talk. I would like to thank Dr. Sandeep Kare, Honorable Manisha Kaye, as organizer of this today's international conference. I am also thankful to scientific committee members for their efficient hard work. I would like to thank Chairman of Jai Hind Comprehensive Educational Institute, Honorable Tata Saheb Gunjar, Director, Honorable Shubhangi Gunjar, Chief Executive Officer, Honorable Dattatreya Galle, Principal, Honorable Dr. Damodar Garkal, and Rajkumar Mankar for enormous cooperation in organizing this event. I also extended my thanks to Microsoft committee members, Mangesh Dhede, Professor Arya, Professor Bhosle, also other committee members for their directly and indirectly involvement for the completion of this work. Also, a big thanks to all the participants of today's international conference for their willingness and their involvement to take on completion of this task. Thank you to all. Thank you. Thanks once again.
thank you, madam. With the permission of Sir Garkal sir, Principal sir, so can we?
Yes, sir. We can conclude.
Yes, sir. So thank you.
Sir, we can conclude.
Okay, sir. Thank you all the participants for joining the today's international conference. So we have to conclude here. Thank you very much. Now you can leave.